Conference will now be recorded.
Good afternoon, all. We will start with our session. So, in today's class, I'm going to give a demo on design for testability, that is DFT. So, let me share my screen. Yeah. So, I'm going to give a demo on design for testability, which is DFT. So, before we go and understand what is DFT, we'll first try to understand what is VLSI. So, VLSI stands for Very Large Scale Integration. VLSI stands for Very Large Scale Integration. Okay, so this is the full form of VLSI, Very Large Scale Integration. Okay, so it means implementation of million transistors in a small area. So that is what is VLSI, implementation of million transistors in a small area. So goals of VLSI. First one is high performance. So high performance, it actually high performance ensuring faster processing. So high performance ensuring faster processing. Okay, so faster processing, and then low power. So optimizing power usage in order to extend the battery life. Okay, so low power is, we are going to optimize the power usage. So optimize power usage to extend battery life, to extend battery life. Okay, so optimizing power usage to extend battery life, and then low area. So low area, it is actually like reducing the chip size in order to achieve compact products. Okay, so reducing the chip size to achieve compact products, to achieve compact products, compact products. Okay. So these are all the goals of VLSI. One is high performance, ensuring faster processing. Other one is low area, so optimizing power usage to extend battery life. And then low area, so reducing the chip size in order to achieve compact products. And this is how our chip will be looking like. Okay. And next, we will go ahead with ASIC flow. So first, we'll try to understand what is the full form of ASIC. So ASIC stands for Application Specific Integrated Circuit. So this is the full form of ASIC, Application Specific Integrated Circuit. So which means it is actually an IC that's custom designed for a particular application. So ASIC stands for Application Specific Integrated Circuit. So it means it is an IC. It is an IC that is custom designed for a particular application. So that's custom designed for a particular application. So an IC that's custom designed for a particular application, for a particular application. Okay, so this is what is ASIC. So full form of ASIC is application specific integrated circuit. Application specific integrated circuit. So which means it is an IC that's custom designed for a particular application. Okay, so if you want to see an example, so say for example, a modern chip. A modern chip, it can't be used as a chip which is used for deployment of airbag in automobile. Okay, so a modern chip can't be used as a chip, which is responsible for deployment of airbag in automobile. Okay, so which is responsible for, or which is used for deployment of airbag in automobile, used for deployment of deployment of airbag in an automobile, in an automobile. Okay, so this is what is called as ASIC, application specific integrated circuit. It is an IC that's custom designed for a particular application specific integrated circuit. So it's an IC that's custom designed for a particular application. So say for example, a modern chip, it can't be used as a chip which is used for deployment of airbag in automobile. Okay, now what is ASIC flow? ASIC flow means it actually gives the steps which we need to follow for designing a chip. Okay, ASIC flow means it gives the steps which we need to follow for designing a chip. So which means they are actually the steps which is involved in the chip design. So ASIC flow is nothing but the steps involved in chip design. Steps involved in chip design gives us the ASIC flow. Okay, so steps involved in chip design is the ASIC flow. Okay, so in the upcoming slide, we will try to discuss about the various steps which is involved in the chip design. Okay, so the first step is the design specification stage. So during design specification stage, what will happen is, based on the application for which we are designing the chip, certain specifications like what has to be the speed, how many memory modules, processors, sensors are required, what has to be the power. So such kind of specifications will be decided. So that is what will happen during the design specification stage. Okay, so based on the application for which we are designing the chip, application for which we are designing the chip, for which we are designing the chip, designing the chip. Okay, so based on the application for which we are designing the chip, certain specifications, okay, certain specifications like what has to be the speed, okay, what has to be the speed, and then how many memory modules, okay, so how many memory modules, how many memory modules, and then processors, processors, and then sensors are required, processors, sensors are required, okay, and then what has to be the power, okay, what has to be the power, what has to be the power, okay, so such kind of specification, okay, so these kind of specifications will be decided during the design specification stage. Okay, so based on the application for which we are designing the chip, certain specifications like what has to be the speed, how many memory modules, processors, sensors are required, what has to be the power. So all those kind of specifications will be decided during the design specification stage. Now, after this, we have the design code stage. Okay, so design code, what will happen? The design team, they will write the design code of the chip. Okay, so design team will write the design code of the chip. Design team, they will write the design code of chip. Will uh, write the design code of the chip. Design code of the chip. Okay, so design team will write the design code of the chip. So what do? They are actually describing the functionality of the chip. They are describing the functionality of the chip. Describing the functionality of the chip. Okay, so they are describing the functionality of the chip. So the design team, they will actually be writing it in behavioral model and data flow level model. So design team, they will actually write in the behavioral and data flow level model form. Okay, so design team will write in behavioral model and data flow level model. Behavioral model and data flow level model. Okay, so data flow level model. Okay, so design team, they will write the design code of the chip. They are actually describing the functionality of the chip. So design team, they will write in behavioral model and data flow level model. Okay, so now after the design team, we have the verification. Verification is actually to validate the functionality of the design. To meet that it requires to ensure that it meets the required specification and performs as intended. Okay, so this is what is done during the verification stage. So verification, what happens? It is actually to validate the functionality of the design. Okay, so it is to validate the functionality of the design. Validate the functionality of the design. Functionality of the design. Okay, to ensure that to ensure that it meets the required specification. It meets the required specification, and performs as intended. And performs as intended. Okay, so this is what happens during the verification stage. So it is to validate the functionality of the design to ensure that it meets the required specifications and performs as intended. Okay, so this is what happens during the verification stage. It's to validate the functionality of the design to ensure that it meets the required specification and performs as intended. So this is what happens during the verification stage. After this, we have the synthesis stage. So during synthesis, what will happen is, so here we had written the behavioral and data flow level model code, right? So here we had the behavioral and data flow level model code. So the behavioral model and data flow level model code, it will get converted to structural form, or we can call it as technology node specific gate level netlist. Okay, so this behavioral model and data flow level model code. So behavioral model and data flow level model code, data flow level model, okay, data flow level model, okay. So this behavioral model and data flow level model code, it gets converted into structural form, or we can call it as a technology node specific gate level netlist. So it will be converted into structural form. It will be converted to a structural form, or we can call it as a technology node specific gate level netlist. Will be converted to a structural form or technology node specific gate level netlist. Specific gate level netlist. Okay, so this is what happens during the synthesis stage. So the behavioral model and data flow level model code, it will get converted into structural form or technology node specific gate level netlist. Okay, and then we have the design for test team. So design for test team, we will discuss in the next slides about this design for testability or design for test team. We will discuss about it in detail in the next slides. So we will understand what is this design for test team in the next slides. Okay. And after that, we have the physical design team. So physical design team, what do? They actually convert this gate level netlist into layout form. Okay, so physical design team, what do? They actually convert the gate level netlist into layout form. Okay, so the gate level netlist is converted into layout form. Is converted into layout form. So this is what happens in the physical design time. So the gate level netlist is converted into layout form. Okay, and after this, we have sign off. So in sign off, we have three things. So one is STA. Okay, so in sign off, we have three things. One is STA, static timing analysis, and then physical verification, PV, and then logical equivalence check, LEC. So we have three things. So one is STA, static timing analysis, physical verification, PV, and logical equivalence check, LEC. So let's try to understand this in the upcoming. So in the next slide, I don't have a space to write it here. So let me just write about this STA, PV, and LEC in the upcoming slides. In the next slide, let me just write it. Okay. So as I'm not having space there, let me just write it in this slide. Okay. So STA. So STA stands for, the full form of STA is static timing analysis. So this is the full form of STA. So full form of STA is static timing analysis. Okay, static timing analysis. So this is the full form of STA. Static timing analysis. So as its name suggests, it is the method of validating the timing performance of a design by checking all possible paths for timing violation. Okay, so STA stands for static timing analysis. So as its name suggests, static timing analysis, as its name suggests, it is a method of validating the timing performance of a design by checking all possible paths for timing violation. Okay, so it is the method of validating the timing performance of the design. Validating the timing performance of the design. Validating the timing performance of a design, timing performance of a design, okay, validating the timing performance of a design by checking all possible paths for timing violations. Okay, by checking all possible paths, by checking all possible paths, all possible paths for timing violations. Okay, so this is what is STA. So STA stands for static timing analysis. As its name suggests, it is a method of validating the timing performance of a design by checking all possible paths for timing violations. Okay, and then we have PV. So PV stands for physical verification. PV stands for physical verification. So physical verification, it is actually to verify the layout of the circuits. Okay, physical verification, it is actually to verify the layout of circuits. So this is to verify the layout of circuits. Verify the layout of circuits. Okay, and then we have LEC. We have LEC. So the full form of LEC is logical equivalence check. Okay, full form of LEC is logical equivalence check. Okay, full form of LEC is logical equivalence check. Equivalence checks. So this is the full form of LEC, logical equivalence check. Okay, so why LEC is actually done? Why LEC is done is our design, it undergoes a lot of changes in each stage. Okay, so our design, it actually undergoes a lot of changes in each stage. So our design undergoes a lot of changes, a lot of changes in each stage, lot of changes in each stage. So if you just see, so first we actually had the behavioral and data flow level model form. So if you just remember the previous slide, so we had seen that first we had the behavioral and data flow level model form, data flow level model code. And later at the time of synthesis, this had actually got converted into technology node specific gate level netlist. Okay, so this actually got converted into technology node specific gate level netlist. So this got converted into technology node specific gate level netlist. Okay, first we had the behavioral and data flow level model code. So that actually got converted into technology node specific gate level netlist. Okay, and then if you're going for low power design, then certain special cells have to be added. So certain special cells for low power design also has to be added. So special cells for low power design, low power design. So like say for example, like clock gating or else isolation cells. So certain things will be added like clock gating and then isolation cells. So certain cells will be added. Okay. So that is what it's like certain special cells for low power design also will be added. Okay, like clock gating cells, isolation cells. So certain special cells required for low power design also will be added. Okay, and then DFT team, we will be adding our own test structures. Okay, so DFT team, DFT like test structures will be added. DFT team, we will be adding our own test structures. So DFT test structures will also be added. DFT test structures are also added. Okay, so if you see, our design undergoes a lot of changes in each stage. So first we had the behavioral and data flow level model code. Then it got converted into technology node specific gate level netlist. And then certain special cells for low power design like clock gating, isolation cells and all will be added. And after that, DFT test structures will also be added. Sorry. So if you see, our design undergoes a lot of changes in each stage. Okay. So that is why LEC is done. So therefore, LEC is done to check whether the final design is logically equivalent to the original design. So our design undergoes a lot of changes in each stage. So that's why LEC is done to check whether the final design is logically equivalent to the original design. Okay, so therefore LEC is done. LEC is done to check whether the final design, whether final design, final design is logically equivalent, is logically equivalent, logically equivalent to original design, original design. Okay, so that is why LEC is done to check whether final design is logically equivalent to the original design. Okay, so that is why LEC is actually done. So if you see our design, it undergoes a lot of changes in each stage. So we had already seen it, and I have also written here. So first we had the behavior and data flow level model code. So that got converted into technology node specific gate level netlist, and certain special cells for low power design will be added, like clock gating, isolation cells. So certain special cells for low power design also will be added. DFT test structures are added. So if you see, our design undergoes a lot of changes in each stage. So sorry, that's why LEC is done to check whether the final design is logically equivalent to the original design. Okay, actually LEC will be performed after each stage. Okay, so LEC is actually performed after each stage. After each stage. Okay, so like after synthesis, after DFT, after PD, like that, after each stage LEC will happen. So after synthesis, and then after DFT insertions, after DFT insertions, and then after PD. So like that, after each stage LEC will happen. Okay, LEC is actually performed after each stage, that is after synthesis, after DFT insertion, after PD, like that. Okay, so this is what happens at the time of this one sign off. So during sign off, we have STA, PV, and LEC. So that is what we had discussed it in the previous slide. STA, PV, LEC. I mean, that is what we had seen in the, that is what I had written and explained about these three steps. What is STA, what is PV, and what is LEC. Okay, and next is we have tape out. So tape out means it is nothing but delivering the database to the manufacturing unit. Tape out means it is to deliver the database to the manufacturing unit. Okay, so delivering the database, okay, to the manufacturing unit, to the manufacturing unit. So this is what is called as tape out. Okay, so delivering the database to the manufacturing unit is called as tape out. And after that, we have packaging and testing. So packaging and testing, it actually happens after manufacturing. Packaging and testing, it happens after manufacturing. Okay, so basically what is packaging? So here if you see, this is how it will be there. So this complete circle will be a wafer, and then the small portion in it is called as the die. Okay, so packaging means covering this die with a protective layer is called as packaging. So packaging means covering this die with a protective layer. So this complete circle, we call it as a wafer, and each small portion we call it as a die. Okay, so covering the die with a protective layer is called as packaging. Okay, covering the die with a protective layer. With a protective layer is called as packaging. Okay, so covering the die with a protective layer. So that is what is called as packaging. So covering the die with a protective layer is called as packaging. And what is testing? Testing means it is actually to check if our chip is good or not. That is, if there are any manufacturing defects or not. So that is what is testing. Testing means it is actually to check if our chip is good or not. If our chip is good or not. Okay, so that is to check whether there are any manufacturing defects or not. That is to check whether there are any manufacturing defects or not. Okay, whether there are any manufacturing defects or not. Manufacturing defects or not. So this is what is called as testing. So testing, it is actually to check if our chip is good or not. That is to check whether there are any manufacturing defects or not. Okay. So this gives the complete ASIC flow. So now in the upcoming slides, we will try to discuss more in detail about this verification, design for testability, and then this testing. Okay, so we will understand more in detail about verification, design for testability, and then this testing. We will try to understand more in detail in the upcoming slides. Okay, so what is DFT? DFT, it is actually to insert some test structures into the design. Like we will be adding our own test structures into the design, like scan insertion, MBIST insertion, boundary scan insertion. Like that, we will be adding our own test structures into the design. Okay, so DFT is to insert test structures into the design, like scan insertion, MBIST insertion, boundary scan insertion, like that. Okay, so DFT is to insert test structures in the design, like scan insertion, embed insertion, boundary scan insertion, like that. We will be adding our own test structures in the design during the pre-silicon stage. So pre-silicon stage means it is nothing but before manufacturing. Pre-silicon stage means it is nothing but before manufacturing. Okay, so to facilitate means to help in the detection of manufacturing defects in the chip. Okay, so DFT is to insert test structures in the design. Like we will be adding our own test structures like scan insertion, embed insertion, boundary scan insertion during the pre-silicon stage. Pre-silicon stage means before manufacturing, to facilitate, that is to help in the detection of manufacturing defects in the chip. So which means if suppose a particular chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay, so if suppose a particular chip a particular chip. Okay, so if suppose a particular chip fails after manufacturing, fails after manufacturing, okay, after manufacturing, okay. So DFT engineers will be able to tell, DFT engineers will be able to tell, okay, DFT engineers will be able to tell, will be able to tell what manufacturing defect has caused the chip to fail. What manufacturing defect has caused the chip to fail, has caused the chip to fail. Okay, so if suppose a particular chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. So that is what DFT is, to insert test structures in the design during the pre-silicon stage to facilitate, that is to help in the detection of manufacturing defects in the chip. So if suppose a particular chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay, so role of DFT engineer. DFT is to insert test structures in the design during the pre-silicon stage to facilitate the detection of manufacturing defects in the chip. Yes, it is the same point which we discussed in the previous slide. Okay, so DFT engineers do not check the functionality of the chip. Okay, DFT engineers do not check the functionality of the chip. We rather check the quality of the chip. Okay, so DFT engineers do not check the functionality of the chip. We rather check the quality of the chip. So what does that mean? We will try to understand here. So uh, okay, so am I audible now?
Yes, now
Am
we
I
can
audible
hear.
now?
Yes, yes, we can hear
Oh,
now.
okay. So yeah, let us just continue. So if you consider this half-added design, so if you consider this half-added design, so sum is A XOR B, carry is AB. Whether this is correct or not, whether this is correct or not, so this is what will be checked by the functional verification team. They will be checking the functionality. Okay, so half-added means sum will be A XOR B, carry will be AB. So whether that is correct or not, that is what will be checked by the functional verification team. They will be checking the functionality. Okay, so by mistake, if someone has written sum is equal to A plus B, carry is equal to AB, someone by mistakenly, if someone has written sum is equal to A plus B, someone mistakenly they have written like this, means then this will not function like a half adder. So this is what will be checked by the functional verification team. They will be checking the functionality. So in our what is it, in our ASIC flow, we had a team called as a verification team over here, right? So that is what they will be checking this. So sum will be, say for example, if you consider half-added design, so sum is equal to A XOR B, carry is equal to AB, whether that is correct or not. So by mistake, if someone has written sum is equal to A plus B, then that will not function like a half-added. So those things is what will be checked by the functional verification team. They will be checking the functionality. Okay, so DFT team, what do? We do not check the functionality. DFT team, we do not check the functionality. We check whether each and every net of the half adder is free of defects or not. Okay, so that is what will be checked by the DFT team. We will check whether each and every net of the half adder is free of defects or not. So say for example, this is what is our intended design. So the half adder design means E and B, it is XOR, so that is what is sum. E and B ANDed, so that is what is carry. So A and B, it is actually coming from some flops, and then sum and carry, it is going back. So A and B, it is coming from some flops, and sum and carry, it is going back again to some flops. So this is what is our intended design. Now suppose during manufacturing, this A net, okay, suppose during manufacturing, unintentionally during manufacturing, A net of this AND gate has got connected to ground like this. Okay, unintentionally during manufacturing, A net of this AND gate has got connected to ground. So these things is what will be checked by the DFT engineer. So DFT team do not check the functionality. We check whether each and every net of the half adder is free of defects or not. So this is what is our intended design. Now suppose during manufacturing, unintentionally during manufacturing, a net of this AND gate has got connected to ground like this. Okay, unintentionally during manufacturing, a net of the AND gate has got connected to ground like this. So this is what will be checked by the DFT. Okay, unintentionally during manufacturing, a net of the AND gate has got connected to ground. So this is what will be checked by the DFT. Okay, so now we will try to understand. We will take up one more example and we will try to understand like some more. We will try to deepen our understanding on what is the difference between a DFT engineer and a functional verification engineer, and why do we need both the DFT team as well as a functional verification team. We will take up another example and we will try to strengthen our understanding on that. Okay, so why do we need DFT team when we have a functional verification team? Okay, why do we need a DFT team when we have a functional verification team? Let's try to understand this point with the help of an example. So in our example, consider that you're having a 10-bit counter. Okay, in your example, say for example, you're having a design. So in your design, you're having a 10-bit counter. In a design, you're having a 10-bit counter with a counter initialization and a counter observation circuit. Okay, so in your design, say for example, you are having a 10-bit counter with a counter initialization and a counter observation circuit. Okay, so this is what is there in your design. So in your design, consider that you are having a 10-bit counter with a counter initialization and a counter observation circuit. Now, scenario is suppose counter is manufactured with a defect. Okay, scenario is suppose counter is manufactured with a defect. So that is why after counting to 999, instead of counting 1000, it incorrectly rolls back to 999. Okay, so suppose counter is manufactured with a defect. So that's why after counting to 999, instead of counting 1000, it incorrectly rolls back to 999. Okay, so now in this case, we will try to understand what will happen if only functional verification team exists and what will happen if a DFT team exists. So both the scenarios we will try to understand. So what we have considered in our example design, we are having a 10-bit counter with a counter initialization and a counter observation circuit. The scenario is suppose the counter is manufactured with a defect. So that's why after counting 999, instead of counting 1000, it incorrectly rolls back to 999. It is again counting 999. Okay, after counting 999, instead of counting 1000, it is again counting 999. So now we'll try to understand what will happen if only functional verification team exists and what will happen if a DFT team exists. Okay, so now what will happen if only functional verification team exists? So in this scenario, what is happening? Counter is actually manufactured with a defect. So that's why after counting 999, instead of counting 1000, it incorrectly rolls back to 999. Okay, after counting 999, instead of counting 1000, it incorrectly rolls back to 999. So now, if only functional verification team exists, then functional team, they will actually test the counter using functional patterns. Okay, we are considering that we are having only functional verification team. So functional team, they will test the counter using functional patterns. So in this example, it will take more than 1000 clock pulses to tell that the counter is failing. So can you tell why will it take more than 1000 clock pulses to tell that the counter is failing in this case? Can anyone guess? Why will it take more than 1000 clock pulses to tell that the counter is failing? In this case, if functional verification team tests the counter,
Maybe they would have missed a condition. It leads to infinite then.
In this case, like counter is manufactured with a defect. So after counting 999, instead of counting 1000, it incorrectly rolls back to 999. So functional team, they are actually testing the counter using functional patterns. So in this scenario, we are considering that only functional verification team exists. So functional team, they are actually testing the counter using functional patterns. So in this case, it will take more than 1000 clock pulses to tell that the counter is failing. So my question is, why will it take more than 1000 clock pulses to tell that the counter is failing in this example?
They may take some clock pulses, like all the test vectors.
Yes, okay. So let's try to discuss it here. So in this case, it will take more than 1000 clock pulses. It will take more than 1000 clock pulses to tell that the counter is failing. So why? Because functional verification team, they will be checking the functionality. Okay, so functional verification team, what do? They will check the functionality. They will check the functionality. Check the functionality. So, which means they will check if the counter counts from 0 to 1023. Okay, they will check the functionality, means in this case it is a 10-bit counter. So that is what do? They will check if the counter counts from 0 to 1023. Okay, they check if the counter counts from 0 to 1023. Counts from 0 to 1023. 0 to 1023. Okay, so that is what. So functional verification team, they will be checking the functionality. That is, they will check if the counter counts from 0 to 1023. Okay, so in this case, what is happening? The counter, it is failing at the 1000th pulse. Okay, so in this case, what is happening? The counter is failing at the 1000th pulse. The counter is failing at the 1000th pulse. Okay, so failing at the 1000th pulse. So why is the counter failing at the 1000th pulse? Because at the 1000th pulse only, it is again counting 999 instead of counting 1000. Okay, the counter is failing at the 1000th pulse because at the 1000th pulse only, counter is again counting 999 instead of 1000. Okay, at the 1000th pulse, at the 1000th pulse, counter is again counting 999 instead of 1000. Counter is again counting 999 instead of 1000. Again counting 999 instead of 1000. Instead of 1000. Okay, so in this case, counter is failing at the 1000th pulse. That is, at the 1000th pulse only, counter is again counting 999 instead of 1000. Okay, so for this itself, 1000 pulses are required. So 1000 pulses are required. Okay, and then some more clock pulses will be required for counter initialization and counter observation. Okay, so some more clock pulses, some more clock pulses will be required for counter initialization and counter observation. Counter initialization and counter observation. And counter observation. So counter initialization means the counter, it has to be brought to some initial state, and counter observation means the output of the counter, it has to be taken to some register, and the register has to be read. Okay, so that is why some more clock pulses will be required for counter initialization and counter observation. So ultimately, we can say that a functional verification team tests the counter using functional patterns. In that case, what will happen? It will take more than 1000 clock pulses to tell that the counter is failing. Okay, and then functional verification team can only tell that the counter is failing. Functional verification team, they can only tell that the counter is failing. The reason is because they will be checking the functionality. Same reason. So functional verification team, okay, functional verification team can only tell that the counter is failing. So the reason is they will be checking the functionality. Okay, they will check the functionality. Okay, they will check the functionality. So in this case, what is happening? That is, check if the counter Sorry, just 1 second. I'll just be back in a minute. Just 1 second. Yeah, sorry about it. Am I audible now? Can anyone confirm if I'm audible?
Yes, you are audible.
Yes, you're audible, ma'am.
Okay, yeah. So let's continue. Sorry about that. So functional verification team, they can only tell that the counter is failing. The reason is because functional verification team, they will be checking the functionality. So that is, they will check if the counter counts from 0 to 1023. They will check if the counter counts from 0 to 1023. 0 to 1023. Okay, 1023 properly or not. So this is what will be checked. Okay, properly or not. So this is what. So functional verification team, they will be checking the functionality. So they will check if the counter counts from 0 to 1023 properly or not. Okay. So in this case, what is happening after counting 999, instead of counting 1000, it is once again counting 999. So counter is failing. In this case, what is happening? In this case, okay, in this case, after counting 999, after counting 999, okay, so in this case, after counting 999, instead of incrementing to 1000, okay, so instead of incrementing to 1000, incrementing to 1000, what is happening? It is once again counting 999. It is once again counting, once again counting 999. It is once again counting 999. So that is what is the issue. So in this case, after counting 999, instead of incrementing to 1000, it is once again counting 999. So the counter is failing. So counter is failing. Counter is failing. Okay. So this is what functional verification team can only tell that the counter is failing because they will check the functionality. They will check if the counter counts from 0 to 1023 properly or not. So in this case, after counting 999, instead of counting 1000, it is once again counting 999. So counter is failing. Okay, so this is what will happen when only functional verification team exists. So if only functional verification team exists in that particular scenario, it will take more than 1000 clock pulses to tell that the counter is failing. And functional verification team, sorry, and functional verification team can only tell that the counter is failing. Now we'll try to understand what will happen if a DFT team exists. Okay, we'll try to understand what will happen if a DFT team exists. So the scenario is the counter, suppose the counter is manufactured with a defect. So after counting 999, instead of counting 1000, it incorrectly rolls back to 999. Okay, so that is what is the scenario we are considering. So suppose the counter is manufactured with a defect. So that's why after counting 999, instead of counting 1000, it is once again counting 999. Now we'll try to understand what will happen if a DFT team exists. So if a DFT team exists, then what will happen? DFT patterns will be used to test the chip. Okay, DFT patterns are used to test the chip. So in that case, DFT will be able to tell that the counter is failing approximately in the range of 100 clock pulses itself. So approximately in the range of 100 clock pulses means you can imagine something like 80, 90, 100, 120, 200, etc. Okay. So DFT will be able to tell that the counter is failing approximately in the range of 100 clock pulses itself, like somewhere around 80, 90, 100, 120, 200, like that. In the range of 100 clock pulses itself, we will be able to tell that the counter is failing. Okay. So if you just observe here, if you just observe, DFT team, if you see, we require significantly less number of clock pulses compared to the functional verification team. So if you just remember what had happened, functional verification team for the same scenario, they had required more than 1000 clock pulses. Okay, so functional verification team for the same scenario, what had happened? They had required more than 1000 clock pulses. They had required more than 1000 clock pulses for the same situation. For the same situation, functional verification team had required more than 1000 clock pulses. Okay, more than 1000 clock pulses. Okay, whereas DFT team, if you see, DFT team, if you see, we approximately require, okay, DFT team, we approximately require in the, so one second. So DFT team, we approximately require in the range of 100 clock pulses. In the range of 100 clock pulses. 100 clock pulses. Okay, that is what. So functional verification team for the same scenario, they had required more than 1000 clock pulses. DFT, if you see, we approximately require in the range of 100 clock pulses. So if you see, DFT team, we require significantly less number of clock pulses compared to the functional verification team. Okay, DFT team requires significantly less number of clock pulses compared to the functional verification team. So that is why what will happen, test time will be less compared to the functional verification team. Okay, that is why test time will be less compared to the functional verification team. So for the same situation, if you see, functional verification team, they had required more than 1000 clock pulses, whereas DFT team, we approximately require in the range of 100 clock pulses. So if you see, DFT team, we require significantly less number of clock cycles compared to the functional verification team. So that is why test time will be less compared to the functional verification team. Okay, and how DFT team are able to tell that the counter is failing approximately in the range of 100 clock pulses itself? How? That is because we will be going for a technique called as scan insertions, because of which we will be easily able to control and observe our circuits. Okay, we will be going for a technique called as scan insertions, because of which we will be easily able to control and observe our circuits. Okay, and when we do the regular course, we will try to understand more in detail what is we will be covering the scan insertions topic, right? So at that time, we will be able to understand this point. Okay, as of now, just remember that in this particular case, so if you see, functional verification team, they require more than 1000 clock pulses, whereas DFT team, we require approximately in the range of 100 clock pulses itself, somewhere around 80, 90, 100, 120, 200, like that, in the range of 100 clock pulses itself. Okay, so if you see how DFT team are able to tell that the counter is failing approximately in the range of 100 clock pulses itself, it is because we will be going for a technique called as scan insertions. So we will be easily able to control and observe our circuit. Okay, so if you say DFT team, we require significantly less number of clock pulses compared to the functional verification team. So that's why test time will be less compared to the functional verification team. Okay, that's why test time will be less compared to the functional verification team. Okay, and then DFT will be able to tell that the counter is failing. Okay, DFT team will be able to tell that the counter is failing, and also tell what manufacturing defect has caused the counter to fail. Okay, DFT team will be able to tell that the counter is failing, and also tell what manufacturing defect has caused the counter to fail. So how? How DFT team are able to tell that? It is because DFT patterns are generated using a technique called as ATPG. Okay, so ATPG tool does fault simulation to generate the test patterns. Okay, ATPG tool does fault simulation to generate the test patterns. And what is fault simulation technique? We will understand it when we do our regular course. Okay, when we do the course, you will be able to understand what is fault simulation technique. Okay, so DFT will be able to tell that the counter is failing, and also tell what manufacturing defect has caused the counter to fail. We can also tell what manufacturing defect has caused the counter to fail. So how DFT team are able to tell what manufacturing defect has caused the counter to fail? It is because DFT patterns are generated using ATPG. So ATPG tool does a technique called as fault simulation in order to generate the test pattern. Okay, ATPG tool does fault simulation to generate the test patterns. Okay, so now, by knowing what manufacturing defect has caused the chip to fail, what we can do is we can actually inform it to the foundry. So if many chips are failing in the same way, then we will be able to, then they will be able to overcome the problem. Okay, so DFT team are able to tell that the counter is failing, and they can also tell what manufacturing defect has caused the counter to fail, right? So by knowing what manufacturing defect has caused the chip to fail, what we can do is, okay, by knowing what manufacturing defect has caused the chip to fail, has caused the chip to fail, okay, has caused the chip to fail. Okay, by knowing what manufacturing defect has caused the chip to fail, what we can do, we can inform it to the foundry. Okay, so we can inform it to the foundry. Okay, we can inform it to the foundry. Okay, so if many chips are failing in the same way, next batch they will try to overcome the problem. Okay, so if many chips are failing in the same way, same way, next batch they will try to overcome the problem. Next batch, they will try to overcome the problem. They will try to overcome the problem. Next batch, they will try to overcome the problem. Okay, so next batch, they will try to overcome the problem. Okay, so how DFT team are able to tell what manufacturing defect has caused the counter to fail? It is because DFT team, we will be generating patterns using ATPG technique. And ATPG tool, it actually does this fault simulation technique to generate the test patterns. So what is fault simulation? We will try to understand when we do the ATPG topic, okay, in our regular course. So by knowing what manufacturing defect has caused the chip to fail, what we can do is we can inform it to the foundry. So if many chips are failing in the same way, next batch they will try to overcome the problem. Okay. So now the conclusion is with the DFT patterns, if you see, test time will be less compared to the functional patterns. Okay, so as we saw in the previous, whatever we have seen in the previous slides, right? So it's the summary of it. So with DFT patterns, test time will be less compared to functional patterns, and then DFT will be able to tell what manufacturing defect has caused the chip to fail. Okay, DFT team will be able to tell what manufacturing defect has caused the chip to fail. So as DFT patterns has these advantages over functional patterns, DFT patterns will be used to test the chip after manufacturing. Some functional patterns also will be used to test the chip after manufacturing, but majority DFT patterns only will be used to test the chip after manufacturing. Okay, so with DFT patterns, test time will be less compared to functional patterns. So DFT will be able to tell what manufacturing defect has caused the chip to fail. So these are the advantages of DFT patterns. So these are the advantages of DFT patterns. So as DFT patterns has these advantages over functional patterns, DFT patterns will be used to test the chip after manufacturing. Some functional patterns will also be used to test the chip after manufacturing, but majority DFT patterns only will be used to test the chip after manufacturing. Okay. So now, if DFT patterns are used to test the chip after manufacturing, why do we need a functional verification team? So if DFT patterns are used to test the chip after manufacturing, why do we need a functional verification team? So let us try to understand this by considering an example. So in our example, I'm having a half adder design. A simple example, let me take a half adder design. So sum is written as A plus B, carry is AB. Whether this is correct? No, this is not correct. This is a functional bug. So sum should have been A XORed with B, carry should have been AB. But here someone mistakenly they have written sum is equal to A plus B, carry is equal to AB. This is a functional bug. So now what will happen? This design only will get synthesized. So this design has got synthesized. For time being, consider that you don't have a functional verification team. Okay, for time being, consider that you don't have a functional verification team. Directly this design has got synthesized like this. Okay, so this is a wrong design. Wrong design has got synthesized, and this design is given to the DFT team. So DFT team, we will generate pattern just to check whether there are any manufacturing defects in each and every net of this design. Okay, this design will be given to the DFT team. DFT team will generate pattern just to check whether there are any manufacturing defects in each and every net of this design. Okay, so now what has happened? Chip has got manufactured. Okay, and now DFT patterns are only applied, and then the output of the chip. So this is the output of the chip. It is compared with the expected output. So output of the chip is also equal to the expected output, which means there are no manufacturing defects. Output of the chip is equal to expected output, which means that there are no manufacturing defects. But whether the circuit will function like a half adder in this case, there are no manufacturing defects. But whether the design will function like a half adder in this case, no, it will not function, because even though there are no manufacturing defects, the circuit will not function like a half adder. Why? The design itself is wrong. Okay, even though there are no manufacturing defects, the circuit will not function like a half adder. Why? The design itself is wrong. Okay, so that is what is the, so initially earlier first stage the design itself was wrong. So sum should have been a XOR with b, but someone mistakenly written sum is equal to a plus b. That's a functional bug. For time being, we assume that there is no functional verification team. Directly, wrong design got synthesized. It was given to DFT team. DFT team will be generating patterns just to check whether there are any manufacturing defects in each and every net of this design. And what will happen? The chip has got manufactured. DFT patterns were applied. Output of the chip was compared with the expected output. Both were equal. Output of the chip was equal to expected output. So, which means there are no manufacturing defects. But whether the circuit will function like a half adder? No. Even though there are no manufacturing defects, the circuit will not function like a half adder. Why? The design itself is wrong. So that is what is the significance of the functional verification team. So they will be validating the functionality. Whatever is written here, so sum is equal to a plus b carries equal to a b, whatever is written here, whether this is correct or not. So that is what will be validated by the functional verification team. Okay, so that is what is the significance of the functional verification team. They will validate the functionality. So whatever is written here, whether this is correct or not, so that is what will be validated by the functional verification team. Okay. So now we have tried to understand what is the difference between the roles of a DFT engineer and then a functional verification engineer. And we have also tried to understand why do we need both the DFT team as well as a functional verification team. Okay, so that is what we had tried to understand. So we have tried to understand what is the difference between a DFT engineer and functional verification engineer's role, and why do we need both DFT team as well as a functional verification team? Why do we require? So that is what we have tried to understand. Okay. So now testing. So testing, it is actually done after manufacturing. So testing is a process of determining whether a device is good or not. So testing includes test pattern generation, application, and output evaluation. So here in this case, these test patterns. These test patterns, it will be generated by the DFT engineer. Before manufacturing itself will be generating the test patterns. So it will be consisting of the input sequence and expected output. So now what will happen? This input sequence, it will be applied onto the chip. So this input sequence will be applied onto the chip, and then the output of the chip. Output of the chip, it will be compared with the expected output. Okay, output of the chip, it will be compared with the expected output. So output of the chip, if it is equal to expected output, means it means that the chip is good. Okay, output of the chip, if it is equal to the expected output, means it means that the chip is good. There are no manufacturing defects. Output of the chip, if it is not equal to the expected output, means it means that the chip has failed. There are some manufacturing defects in the chip. Okay, so these test patterns, it will be generated by the DFT engineer before manufacturing itself. So it will be consisting of the input sequence and expected output. The input sequence will be applied onto the chip, and then the output of the chip will be compared with the expected output. So output of the chip, if it is equal to expected output, means it means that the chip is good. There are no manufacturing defects. Output of chip, if it is not equal to the expected output, means it means that the chip has failed. There are some manufacturing defects in the chip. Okay, output of the chip, if it is not equal to the expected output, means it means that the chip has failed. There are some manufacturing defects in the chip. Okay, so if a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay, if a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay, so now let us try to understand what are called as manufacturing defects. Manufacturing defects means these are the defects that are caused due to process variations and random imperfections. Okay, manufacturing defects means these are the defects that are caused due to process variations and random imperfections. So process variations means slight variation in the transistor channel length. Okay, so slight variation in the transistor channel length. Okay, slight variation in the transistor channel length. Okay, metal interconnect width and thickness. Okay, so metal interconnect width and thickness. Metal interconnect width and thickness. Okay, metal interconnect width and thickness. So all these things will impact the logical and timing performance. So all these things can will impact the logical and timing performance. Impact the logical and timing performance. Okay, logical and timing performance. Okay, so that is what. So manufacturing defects means these are the defects that are caused due to process variation. So process variation is slight variation in transistor channel length, metal interconnect width and thickness. All those things will impact the logical and timing performance. Okay. And then we have the random imperfections. Random imperfections means it can result in unintentional shorts, unintentional opens, all those things. Okay. So it can actually result in result in okay shorts, opens, all those things, unintentional shorts, unintentional opens, all those things. Okay, it can actually result in unintentional shorts, unintentional opens, all those things. Okay, so this is what is manufacturing defect. And now we'll try to understand the flow of DFT. So flow of DFT is first is insertion. So it is nothing but adding the extra logic. And next is generation. Generation, that is patterns will be generated. So input data and expected output will be generated. And then we have the simulation validation. So which is nothing but simulation. We'll try to understand this complete flow as well as the course overview. So what are the topics which is covered in our course and those things both in theory as well as labs. What are the contents? What are the course contents? What are the contents which will be covered in our course? We will try to understand it in the upcoming slides. Okay. So this is what is our course outline. So first we will be starting off with scan insertions. Then we have scan compression, on-chip clock controller, OCC logic, automatic test pattern generation, ATPG, simulations. So simulation as of now, no timing simulation is covered. So in simulation as of now, no timing simulation. No timing simulation is covered. Okay, so as of now, no timing simulation is covered in our course. Okay, and next is JTAG. JTAG stands for Joint Test Action Group. Okay, and then memory built-in self-test, and then boundary scan, B scan, that is boundary scan. So this JTAG is actually a IEEE 1149.1 standard. Okay, this JTAG is a IEEE 1149.1 standard. Okay, we will also be covering IJTAG. We will also be covering IJTAG, which is nothing but IEEE 1687 standard. Okay, I have not included it in our demo PPT because in order to understand what is IJTAG, you need to know JTAG in detail. So that is why in this overview or demo PPT, I have not included this IJTAG, but in our regular course, we will be covering. Okay, so we will be covering JTAG, which is nothing but IEEE 1149.1 standard, as well as we will be covering IJTAG, so which is nothing but a IEEE 1687 standard. So both the things we will be covering. Okay, so now we can have a short break for 10 minutes and then we will try to see what are all the topics which is there in this course. So what is our course outline? We will try to understand what are the topics which is there in this course outline. We will see an overview about each of these topics and we'll also see inside. So scan insertion is the main topic. Inside scan insertion, what are all the subtopics will be covered. So we will try to understand it. So we can have a short break for 10 minutes. So now time is 3:08. We can have a break till 3:18 and then we will cover what are all the topics which is covered in our course outline. So this is the course outline. We'll discuss in detail about each of these topics, a short overview about each of these topics, and also what will be covered in their subtopics. So all those things we will try to understand it after the break. Okay, so thank you all. We will meet after the short break at 3:18. Okay, so we'll have a short break for 10 minutes and we will meet at 3:18 after the break. Okay, so thank you all. Good afternoon, all. We will continue with our session. Can anyone confirm if I am audible and is my voice clear?
Yes, audible, ma'am.
Okay, so now let us continue with our discussion. So now we will discuss the course outline, like what are the topics which is covered in our course, and we will see a brief idea on those topics. Okay, so the first topic is scan insertion. Okay, so scan insertion means what happens is all the normal flops, they will be converted into a scan flop. And these scan flops, they will be stitched into a scan chain. Okay, so all the normal flops, they will be converted into scan flops, and these scan flops, they will be stitched into a scan chain like this. Okay, so now what is a scan flop? What is a how the scan flops are stitched into a scan chain? What is a scan chain? How does a scan chain function? All those things we will try to discuss it in the next session. When we do the course. Okay, so as of now, just remember that scan insertion means all the normal flops, it will be converted into scan flops, and these scan flops will be stitched into scan chains. Now, what is the need of scan insertion? Why do we have to convert all the normal flop to scan flops? And why do we have to stitch the scan flops into a scan chain? So why do we have to do that? Let us try to understand. Okay. So why do we have to replace all the normal flop with scan flops? Why do we have to stitch the scan flops into a scan chain? Why it should be done? We will try to discuss it in the next slide. Okay. So what is the need of scan insertion? Need of scan insertion is actually to gain controllability and observability of the design. Okay, so to gain controllability and observability of the design, so which means in order to easily control and observe our circuit, we will be going for scan insertions. So need of scan insertion is to gain controllability and observability of the design. Okay, so which means in order to easily control and observe our circuit, we will be going for scan insertions. So the example to understand the need of scan insertion is the same counter example which we had taken in the previous slide. So in my design, I'm having a 10-bit counter with a counter initialization and a counter observation circuit. So suppose counter is failing at suppose if the counter is failing, so which means after counting 999 instead of counting 1000, it again counts 999. Okay, suppose if the counter is failing after counting 999 instead of counting 1000, it again counts 999. So, how many clock pulses are required by functional verification team and DFT team to find out that the counter is failing? So, functional verification team, they require more than 1000 clock pulses to detect that the counter is failing. So, why we had already discussed it in the previous slides itself, before the break itself, we have tried to understand it. Okay, so in this scenario, functional verification team, they require more than 1000 clock pulses to tell that the counter is failing. Why we had already understood it before the break itself, we had tried to understand this. Okay. DFT team will be able to tell that the counter is failing approximately in the range of 100 clock pulses. Okay, so DFT team will be able to tell that the counter is failing approximately in the range of 100 clock pulses. Okay, so approximately in the range of 100 clock pulses means somewhere around like 80, 90, 100, etc. Okay, so 100, 120, like that, approximately in the range of 100 clock pulses, we will be able to tell that the counter is failing. So, which means if you see DFT team, we are able to tell that the counter is failing significantly less number of clock cycles as compared to the functional verification team. Okay, so DFT team are able to tell that the counter is failing significantly less number of clock pulses compared to the functional verification team. Okay, so in significantly less number of clock pulses. So in significantly less number of clock pulses, clock cycles compared to the functional verification team. Okay, so compared to the functional verification team, compared to the functional verification team, as you can see here. Okay, so now how? How DFT team are able to tell that the counter is failing in significantly less number of clock cycles as compared to the functional verification team? So how? It is because DFT team go for a technique called as scan insertion. DFT team will go for a technique called as scan insertion. Because of that, we will be easily able to control and observe our circuit. So in order to understand how we are able to tell that the counter is failing in significantly less number of clock cycles, compared to functional verification team. That is, in this example, how we are able to tell that the counter is failing approximately in the range of 100 clock pulses itself. How? In order to understand that, you need to know what is a scan cell, what is a scan chain, how a scan chain functions. All those things you need to know. So that's why when we do the course, when we do our DFT course, we will once again revisit the same example. Okay, when we do the scan insertion topic, we will once again revisit the same example. And at that time, we would have covered what is a scan cell, what is a scan chain, how a scan chain functions, all those things we would have covered it. So at that time, you will be able to understand how in this particular case DFT team is able to tell that the counter is failing approximately in the range of 100 clock pulses itself. So how we will be able to tell that? Okay, so we will be discussing it in our course. Okay, so for that, in order to understand how, you need to know what is the functionality of a scan cell, what is the functionality of a scan chain, all those things. Only then you'll be able to understand how. So we will discuss it during the course. Okay, so this is what is scan insertion. So DFT team, we go for a technique called as scan insertion. Because of that, we are able to easily control and observe our circuit. Because of that, in this particular example, we are able to tell that the counter is failing approximately in the range of 100 clock pulses itself. So which means we require significantly less number of clock cycles compared to the functional verification team. Okay, so as a part of the scan insertion topic, these are all the subtopics will be covered. Okay, so in our scan insertion portion of our training, these are all the subtopics which we will be covering. So the first one is we will be covering the scan cell functionality and scan chain functionality. Okay, we will cover the scan cell functionality. Okay, we will cover the scan cell functionality, and then we will cover the scan chain functionality. Scan chain functionality. Okay, so we will cover the scan cell functionality and scan chain functionality, and then we will cover the need of scan insertion. We will cover the need of scan insertion. Okay, so that is in order to easily control and observe our circuit, right? So as I told, we will once again revisit the same counter example in our course. Okay, the counter example which we discussed now, we will again revisit the same example when we do our course, and at that time we will show you how DFT team are able to tell that the counter is failing approximately in the range of 100 clock pulses itself. How? We will show you that by taking some values. Okay, we will show you and we will explain the need of scan insertion. So that is what we will be covering, the need of scan insertions. And then basically in scan insertion, what will happen? All the normal flops in the design. So all the normal flops in the design, it has to be converted into a scan flop. So all the normal flops in the design, it has to be converted to a scan flop. So the normal flops in the design, if it has to be converted to a scan flop, then what it has to do? It has to pass certain rules. It has to pass certain rules. Okay, so if a normal flop in the design, if it has to be converted to a scan flop, then it has to pass certain rules. So those rules are only called as scan DRCs, design rule checks. So those rules are only called as scan DRCs. So scan DRCs means design rule checks. Design rule checks. Okay, so scan DRCs are nothing but design rule checks. Okay, so there will be various scan DRCs like clock controllability DRC. Okay, there will be various scan DRCs like clock controllability DRC, and then we have the set reset controllability DRC. Okay, we will be having the set reset controllability DRC. Okay, and then we will be having the potential race DRC. We'll be having the potential race DRC. Okay, so potential race DRC, and then we will be having the feedback loop DRC. We'll be having the feedback loop DRC. Okay, and then we will be having the X source DRC. Okay, we will be having the X source DRC, and we will also be having the bus contention DRC. Okay, so bus contention. So all these things. So there will be various scan DRCs. Okay, so if a normal flop in the design, if it has to be converted to a scan flop, then it has to pass certain rules. So those rules are only called as the scan DRCs. DRCs, the full form of DRC is design rule checks. So there will be various scan DRCs like clock controllability, set reset controllability, potential trace, feedback loop, edge source, bus contention, like that. There will be various scan DRCs. So we will be covering all those scan DRCs in our course. Okay. So that is what is the third topic in our scan insertion topic. Okay. And then the fourth topic which we will be covering in our scan insertion courses, scan insertion topic is scan chain balancing. Okay, we will be covering scan chain balancing. Okay, so what is called as scan chain balancing? Okay, what is called as scan chain balancing? Scan chain balancing means keeping almost equal number of flops in the scan chain. That is what is called as scan chain balancing. Okay, scan chain balancing. What is scan chain balancing? Scan chain balancing means keeping almost equal number of flops in the scan chain. Okay, so keeping almost equal number of flops, almost equal number of flops, equal number of flops in the scan chain. So that is what is called as scan chain balancing. So scan chain balancing means keeping almost equal number of flops in the scan chain. So that is what is called as scan chain balancing. So say for example, you are having one scan chain. In scan chain 1, you are having like 1000 flops, and then scan chain 2, you are having 1000 flops. Scan chain 3, say for example, you are having 999 flops. Like this, if it is there means then these scan chains are called as the balanced scan chains. These scan chains are the balanced scan chains. Okay, so scan chain balancing. Scan chain balancing means keeping almost equal number of flops in the scan chain. So if you see in this scan chain, almost equal number of flops are there. In two scan chains, you are having 1000 flops, and in scan chain 3, you are having 999 flops. So in this case, the scan chains are balanced. Okay. Now, why are we going for scan chain balancing? Why do we need to go for scan chain balancing? We need to go for scan chain balancing in order to reduce test time. Okay, we need to go for scan chain balancing in order to reduce the test time. So this is to reduce the test time. To reduce the test time. Okay, we will be going for scan chain balancing in order to reduce the test time. And how? How if you go for scan chain balancing, you are able to achieve reduction in test time? We will discuss in the course. Okay, we will actually discuss in course. We will discuss in course. Okay, so what is scan chain? So why we are going for scan chain balancing? We are going for scan chain balancing in order to reduce the test time. And how if you go for scan chain balancing, you are able to achieve reduction in test time? We will discuss it in our course. Okay, we will discuss it in our course. Okay, now in order to achieve scan chain balancing, we again have to adopt certain techniques called as edge mixing and domain mixing. Okay, so in order to achieve scan chain balancing, in order to achieve balancing, okay, in order to achieve balancing, okay, we need to adopt edge mixing and domain mixing. Okay, we need to adopt, okay, we need to adopt edge mixing and domain mixing. We need to adopt edge mixing and domain mixing. Okay, we need to adopt edge mixing and domain mixing. Okay, so in order to achieve scan chain balancing, we need to adopt edge mixing and domain mixing. So, what is edge mixing? What is domain mixing? And how, if you go for edge mixing and domain mixing, you are able to achieve balanced scan chains? We will discuss it when we do the course. Okay, so in order to achieve scan chain balancing, we need to adopt edge mixing and domain mixing technique. So what is edge mixing? What is domain mixing? And how if you go for edge mixing and domain mixing, you are able to achieve balanced scan chains? We will understand it when we do the course. So this is what is our fourth topic, scan chain balancing. Okay, and then next topic what we will discuss is, if you go for this edge mixing and domain mixing technique, so okay, if you go for this edge mixing and domain mixing technique, it will again introduce some problems. So that is what we will discuss. So what are the problems which we will encounter when we have the edge mixing, when we go for edge mixing and domain mixing, and what are the solutions for it? That is what we will try to understand. Okay, so what are the problems? What are the problems in edge mixing and domain mixing? What are the problems in edge mixing and domain mixing? Okay, what are the problems in edge mixing and domain mixing, and what are the solutions? What are the solutions? We will try to understand what are the solutions of those problems. Okay, so that is what we will understand next. Okay, we will try to understand what are the problems in edge mixing and domain mixing, and what are the solutions of it, how to overcome those problems. So that is what we will be understanding next, problems in edge mixing and domain mixing, and what are the solutions. So that is what we will be understanding as a next topic. Okay, so these are all the main topics which is covered in the scan insertion topic. So our first topic, so topic 1 is scan insertion. So topic 1 which we will be covering in our course is scan insertion. So in this topic, these are all the main subtopics which we will be covering. So first we will cover what is a scan cell and what is a scan chain and what are the functionalities of it. We will then cover the need of scan insertion. As I told, we will once again revisit that counter example, and we will try to understand how DFT team are able to tell that the counter is failing in approximately in the range of 100 clock pulses. So we will show you that. So that is what is the need of scan insertion. We'll try to understand. And then if a normal flop, if it has to be converted to a scan flop, then it has to pass certain rules. So those rules are only called as the scan DRCs, design rule checks. So there will be various scan DRCs as I have listed here. So we will be covering all these scan DRCs. Okay, and then we will also understand about this topic called as scan chain balancing. What is scan chain balancing? Keeping almost equal number of flops in the scan chain is called as scan chain balancing. And why do we need to go for scan chain balancing? We need to go for scan chain balancing in order to reduce test time. So how, if you go for scan chain balancing, you are able to achieve reduction in test time? We will discuss it in our course. And in order to achieve scan chain balancing, we need to adopt the edge mixing and domain mixing. So what is edge mixing? What is domain mixing? And how, if you adopt edge mixing and domain mixing, you are able to achieve balanced scan chains? All those things we will discuss it in our course. Okay, and then if you go for edge mixing and domain mixing, again it will introduce some problems. So what problems edge mixing and domain mixing will introduce again, and what will be the solution, how we are going to overcome that problem? So that is what we are going to discuss. So problems in edge mixing and domain mixing, and then their solution. So that is what we are going to understand. Okay, so this is what is the first topic, which is nothing but the scan insertion topic. The next topic is scan compression. So scan compression means a single scan channel is internally divided into multiple scan chains. So which means we can say that the internal chains, so we can say that that is what we can say. The internal scan chains are compressed into external channels. We can say that the internal scan chains. Okay, both are correct. A single scan channel is internally divided into multiple scan chain is also correct. We can also say it as internal scan chains. Internal scan chains are compressed into external channels. Are compressed into external channels. Compressed into external channels. Okay, compressed into external channels. So that is what it means. Internal scan chains are compressed into external channels. Okay, so which means, say for example, you are having these internal scan chains. So the scan chains, we will be calling it as internal scan chains. So these are all your scan chains. Okay, so these are all your internal scan chains. So these are your internal scan chains. So these internal scan chains, what will happen? They will be compressed into external channels. So these internal scan chains, what will happen? They will be compressed into external channels like this. They will be compressed into external channel. So this is what is external channel. So this is external channel input. Okay, so this is external channel input, and this is external channel output. Okay, so the internal scan chains. So the scan chains, we call it as the internal scan chains. These internal scan chains, they are compressed into external channel. So if you see, they are compressed into external channel. So this is external channel input, this is external channel output. They are compressed into external channels. Okay, so why do you need to go for scan compression? Why do you need to compress the internal chains into external channels? Why do you need to do that? You need to do that in order to reduce the test time and in order to reduce the test data volume. So test data volume, what does test data volume mean? Test data volume means number of bits of patterns. Okay, test data volume means number of bits of patterns. So that is what is test data volume. Okay, so we will be going for scan compression in order to reduce the test time and in order to reduce the test data volume. Test data volume means it is nothing but the number of bits of patterns. So how? How if you go for scan compression? How if you go for scan compression, you are able to reduce the test time and you are able to reduce the test data volume? How? How is it? How are we able to do that? So we will understand it logically. Logically also we will try to understand, and we will also take up some formula. We will also take up the formula for test time and we will take up the formula for test data volume. We will substitute the values in those formulas and we will show you that if you go for scan compression, you are able to achieve reduction in test time and reduction in test data volume. Okay, so we will cover how we will cover it in our course. So we will try to understand it logically. Also, we'll try to understand. We'll also use the formula and we'll try to understand. So we'll take the formula for test time. We will take the formula for test data volume. We will substitute the values of the various quantities in that formula, and then we will show you if you go for compression, you are able to achieve reduction in test time and you're able to achieve reduction in test data volume. Okay, so yeah, now you have understood what is scan compression. So the scan chains, that is nothing but the internal chains, they are compressed into external channels and we are doing it in order to reduce the test time and in order to reduce the test data volume. Okay, so now in order to achieve scan compression, okay, to achieve scan compression, if you are using mentor graphics tools means, then you will be adding up a logic called as EDT logic. Okay, so to achieve compression, to achieve compression, okay, to achieve compression, so if you are using like mentor graphics tools, while using mentor graphics tools, okay, while using mentor graphics tools, okay, mentor graphic tools, okay, we need to add up a logic called as EDT logic. Okay, we need to add up a logic called as EDT logic. Okay, so in order to achieve scan compression by using mentor graphics tools, you need to add up a logic called as EDT logic. Okay, just one second. Okay, yeah, sorry about it. Am I audible? Is my voice clear? Am I audible? Is my voice clear? Can anyone confirm that?
Yes, ma'am.
Okay, so yeah, now let us try to understand this. Okay, so in order to achieve scan compression, if you are using mentor graphics tools, then you need to add up a logic called as EDT logic. So the full form of EDT is embedded deterministic test. Okay, full form of EDT is embedded deterministic test. Okay, so embedded deterministic test, deterministic deterministic test. Okay, so the full form of EDT is embedded deterministic test. Okay, so inside this EDT logic, you will be having four components. Like one is the decompressor component. Okay, within this EDT logic, you will again be having certain components called as the decompressor components, and then you have the compressor component. Okay, you have the compressor component, and then you have the controller component, controller, and after that you have the bypass logic. So these are all the components of EDT logic. These are all the components of EDT, like decompressor, compressor, controller, and bypass logic. Okay, these are the four components of EDT logic. Okay, like this. So here in this case, these are your internal chains. So these are your internal chains. So these internal chains, if you see, they are compressed into external channels. So if you see, they are compressed into this external channels like this. So these internal chains in this picture. So if you see, they are compressed into that external channel. So in between, if you see, you have this decompressor component and you have this compressor component, right? You have the decompressor and compressor component. Okay, so that is what is actually present inside your. These decompressor and compressor components are nothing but a part of the EDT logic. Okay, and apart from that, you also have certain components like controller and bypass logic. I have not drawn the entire structure here. Okay, here I have not drawn the entire structure of the EDT logic. When we do the course, I will give you the complete structure of the EDT logic along with all the components included. Okay, so internal chains are compressed into external channels. That is what is called as scan compression. So in order to achieve scan compression, if you are using mentor graphics tools, you will be adding up a logic called as EDT logic. So the full form of EDT is embedded deterministic test. So inside the EDT logic, you'll be having various other components. Like inside the EDT logic, you'll be having the components like decompressor, compressor, controller, bypass logic. These are all the components which is present inside the EDT logic. Okay, decompressor, compressor, controller, bypass logic. Okay, so in this picture, if you see, these are the internal chains. These internal chains are compressed into two external channels, right? And in between, if you see, you're able to see the decompressor component, you're able to see this compressor component. So these are all the part of the EDT logic. So this decompressor and compressor are nothing but a part of the EDT logic. Apart from this, you also have the controller as well as bypass logic in the EDT logic, but I have not represented all the components of the EDT logic in this picture. When we do the course, I will show you a structure of the EDT logic with all the components which is present. Okay. So now, as a part of our EDT training, okay, so as a part of our EDT training, okay, scan compression training as a part of our EDT training, what are all the topics we will be covering is, okay, so our topic 2, our main topic 2 is scan compression. Topic 2 is scan compression. So in our scan compression topic, what are all the topics we will be covering is, okay, internally what are the subtopics we will be covering is, first we will try to understand what is scan compression. Okay, we will try to understand what is scan compression. Okay, what is scan compression, we'll try to understand. Okay, so already we have discussed here, right? The internal chains are compressed into external channels. That is what is scan compression we will understand. And then it's need. So what is the need of, scan compression? What is the need of scan compression? Okay. Sorry, what is scan compression? What is scan compression? We will try to understand. What is scan compression? So the internal scan chains, they are compressed into external channels. Already we have discussed, right? So that is what we'll be covering it. So what is scan compression? We will understand. And then the need of scan compression. So need of scan compression, we will try to understand. So what is the need of scan compression? One is reduction in test time and the other one is reduction in test data volume. Okay, we will understand reduction in test time. Okay, reduction in test time. Okay, reduction in test time, reduction in test data volume. So this is what is the need of scan compression, reduction in test time and reduction in test data volume, reduction in test data volume. Okay, so this is what we will be covering in our course. So how we will cover it, how logically also we will cover. Okay, logically also we will, and we will also cover it using formula. Okay, so 1 second, I am getting a prompt that my voice has got disconnected. Am I audible? Because I got a prompt that my voice got disconnected.
It's audible only.
Okay, yeah. So if in case my voice gets disconnected, you can like unmute yourself and let me know. Okay. So yeah, so how we will try to understand it logically, and we will also understand it using formula. We will also understand it using formula. Okay, both logically as well as using formula, we will try to understand it. Okay, the need of scan compression. Okay, and then there will be a quantity called as compression ratio. There will be a quantity called as compression ratio. So compression ratio quantity is number of internal chains. So number of internal chains divided by number of external channels. So compression ratio quantity is number of internal chains divided by number of external channels, number of external channels. So that is what is compression ratio. Okay. So number of internal chains divided by number of external channels. So this is what is the compression ratio formula. Okay. So now in this compression ratio, what we will try to understand is, we will usually make sure that compression ratio doesn't exceed 100x. We will usually make sure that compression ratio doesn't exceed 100x. Okay, we will usually make sure that compression ratio doesn't exceed 100x. Okay, doesn't exceed 100x. So this is what? Why? Why? We will try to understand. Okay, why do we usually make sure that compression ratio doesn't exceed 100x? So compression ratio formula is number of internal chains divided by number of external channels. So we usually make sure that compression ratio doesn't exceed 100x. So why? We will try to understand. Why is it like that? We'll try to understand. And we'll also try to understand about the merits and demerits of high and low compression ratio. We will try to understand the merits and demerits of high and low compression ratio. We'll try to understand the merits and demerits of high and low compression ratio. Okay, high and low compression ratio we will try to understand. Okay, we will try to understand the merits and demerits of high and low compression ratio. Okay, so all these things, all these points, we will try to understand it in the compression ratio topic. After that, we will understand about the EDT logic. So EDT logic. So in order to achieve scan compression, if you're using mentor graphics tools, then you will be adding up a logic called as EDT logic, which is embedded deterministic test, as we discussed in the previous slide. So inside the EDT logic, you will be having various components like decompressor. Okay, so decompressor component, and then you have the compressor component, decompressor, and then you have the compressor, and then you have the bypass logic, controller logic, and then you have the bypass logic, controller, and then you have the bypass logic. So we will discuss about all these components in detail, like decompressor means what is the structure of decompressor, what role it plays in compression. Same way, compressor means what is the structure of compressor, what role it plays in compression. Same way, controller logic, what is the bypass logic, all those things about each and every component of the EDT logic, we will understand it when we do the scan compression topic. Okay, and then we will also understand about some small topics like pipeline flops in EDT. So sorry, pipeline flops in compressor. Okay, we will understand some small topics like pipeline flops in compressor, and then lockup cells in EDT, lockup cells in EDT. Okay, so some kind of small topic, these kind of small topics we will try to understand. Okay, so these are all the topics which we will be covering it in our course, in our scan compression topic. So basically we'll be covering what is scan compression and the need of scan compression, and we will also cover a quantity called as compression ratio. So the formula for compression ratio is number of internal chains divided by number of external channels. So this compression ratio quantity, we usually make sure that compression ratio doesn't exceed 100x. So why? We will try to understand, and we will also try to understand about the merits and demerits of high and low compression ratio. And then whenever you are going for scan compression, you will be adding up, in order to achieve scan compression, if you are using mentor graphics tools, you will be adding up a logic called as EDT logic, which is embedded deterministic test. So inside the EDT logic, you have these components like decompressor, compressor, controller, bypass logic. So we will understand the structure and functionality of each and every component, and we'll try to understand how we are able to achieve like what role it plays in scan compression. Each of these components play in scan compression, we will try to understand. And next we will try to understand certain small topics like what are called as pipeline flops in compressor, and what are the lockup cells in EDT. So such kind of small topics we will try to cover it in our scan compression topic next. Okay, so these are the things which we'll be covering it in our scan compression topic. Next is ATPG. So ATPG stands for automatic test pattern generation. Okay, so ATPG stands for automatic test pattern generation. Okay, so as its name suggests, automatic test pattern generation. So as its name suggests, it is a process of generating test patterns for a given fault model. So full form of ATPG is automatic test pattern generation. So as its name suggests, it is a process of generating test patterns for a given fault model. Like there will be various fault models like StuckAt, TDF, PDF, IDDQ, like that there will be various fault models. So it is a process of generating test patterns for a given fault model. Okay. So during ATPG, what will happen? Test patterns will be generated. Okay. During ATPG, what will happen? Test patterns will be generated. So these test patterns will be used to test the chip after manufacturing. Okay. So after manufacturing, if suppose there are any defects, these test patterns should have the capability to detect most of the manufacturing defects. Okay, during ATPG, what will happen? Test patterns will be generated. So these test patterns will be used to test the chip after manufacturing. So after manufacturing, if suppose there are any defects, these test patterns should have the capability to detect most of the manufacturing defects. So how are we sure? How are we sure that our test patterns will be able to detect most of the manufacturing defects? Okay, how are we sure that our test patterns will be able to detect most of the manufacturing defects? It is because our tool does a process called as fault simulation in order to generate the test patterns. So this fault simulation is actually not a very straightforward topic. So we will take some two sessions to completely understand this fault simulation topic. So fault simulation is not a straightforward topic. So that's why I have not kept a overview of fault simulation in the demo class. In the main course, we will take somewhere around two sessions in order to understand this fault simulation topic. Okay, so as of now, just understand that what is ATPG? ATPG is automatic test pattern generation. So during ATPG, test patterns will be generated. So these test patterns only will be used to test the chip after manufacturing. So after manufacturing, if suppose there are any defects, these test patterns should have the capability to detect most of the manufacturing defects. Now, how are we sure that our test patterns will be able to detect most of the manufacturing defects? So it is because our tool does a process called as fault simulation to generate the test patterns. Okay, how are we sure that our test patterns will be able to detect most of the manufacturing defects? It is because our tool does a process called as fault simulation to generate the test patterns. Okay, so ATPG is actually a very vast topic, and it's also those fault simulation, all those things are also not a very straightforward topic. So ATPG might take around 10 to 12 sessions to complete. Okay, so the third topic is ATPG. So topic 3 is ATPG. So it is a very vast topic. ATPG is a very vast topic, and those kind of fault simulation, all those things are also not a very straightforward topic. So that is why we will it will take around 10 to 12 sessions to complete. Okay, fault simulations are all not a straightforward topic. So we will take around 10 to 12 sessions to cover the ATPG concepts. Okay, so I'll just give you a brief idea on what are all the topics, subtopics we will be covering it as a part of our ATPG course. So first we will try to understand like what is ATPG and fault simulation. Okay, what is ATPG and then what is that fault simulation? All those things we will try to understand. What is ATPG? What is fault simulation? We'll try to understand. So as I told, fault simulation is not a straightforward topic. So in order to understand it, it might take 2 sessions to understand that. Okay, so we will understand what is ATPG. We will understand what is fault simulation. So that is what we'll first understand. And then we will be covering the fault models. We'll be covering the various fault models. So there will be various fault models like stuck at fault model. Okay, stuck at fault model. TDF, transition delay fault model. PDF, path delay fault model. And then IDDQ fault model. IDDQ fault model. So this TDF fault model and PDF fault model are also called as at speed test. Okay, so this TDF and PDF are also called as at speed test. Okay, so this TDF and PDF are the at speed test. Okay, and we will also be covering the certain topics like fault dominance, fault equivalence, and fault collapse. Okay, we'll be understanding what is fault dominance. Okay, fault dominance, and then fault equivalence. Okay, fault equivalence. Okay, fault equivalence, and then fault collapse. We will try to understand what is it, fault collapse. Okay, and then like we will be understanding like fault aliasing. What is fault aliasing? Okay, what is fault aliasing? And then we will try to understand what is coverage, what is fault coverage, what is test coverage, all those things we will understand. What is fault coverage, what is test coverage? Okay, and then we will be understanding about a topic called as fault classes, which is actually a very important topic. Fault classes we will try to understand. So fault classes, so basically faults, they are broadly classified into testable faults and untestable faults. Okay, so the faults, they are broadly classified into testable faults and untestable faults. So testable faults and then untestable faults. So faults are broadly classified into testable faults and untestable faults. So in untestable, again, you have these subclasses, like you have the unused, and you have tied, and then you have blocked, and then you have redundant. Okay, unused, tied, blocked, redundant. These are all the subclasses of untestable class of faults. So under untestable, you have this unused type, blocked, redundant. Okay, under untestable, these are the subclasses: unused type, blocked, redundant. So we'll try to understand about each of these fault classes. Under testable class, you have this detected. Okay, so under testable class, you have detected class, possibly detected class, ATPG untestable class, ATPG untestable class. Okay, ATPG untestable class, and then undetected class. So all those things you have. So under testable class, again you have these subclasses like detected, possibly detected, ATPG untestable, undetected. So these are all the subclasses of testable class of fault. Okay, so we will also be understanding about test point insertion. Okay, so this fault classes, this complete fault classes topic is an important topic. So we'll be understanding this fault classes topic in detail. Okay, and then we will also be understanding about test point insertion. Okay, we will also be understanding about test point insertions. We will also be understanding about the pattern classification topic. Pattern classification topic. Okay, pattern classification. And then like we'll be covering like what are the ways of detecting TDF faults. Okay, what are the ways of detecting TDF faults? Okay, we'll be covering what are the ways of detecting the TDF faults. So, which is nothing but LOC and LOS technique, LOC technique, LOS technique we'll be covering. So, ways of detecting TDF faults, LOC technique, LOS technique will be covering. And when we cover the LOS technique, we will also be understanding about the pipeline scan enable architecture. So, what is that pipeline scan enable architecture? We'll try to understand. Okay, we will be understanding about like on-chip clock controller, OCC. So we'll also be covering on-chip clock controller. Okay, on-chip clock controller, that is nothing but the OCC logic. So we will be covering its internal architecture. Okay, we'll be covering its architecture, and we will also be covering the placement of OCC topic will be covering. Okay, the internal architecture of OCC, and then the placement of OCC topic will be covering it. We will also be covering like what is called as dead cycles. We will be covering. Okay, so what is called as dead cycles. Okay, so all those things we will be covering. Okay, and then we will also be covering about these what is it, timing exceptions. We will also be covering about these timing exceptions. So timing exceptions are nothing but that false path and multi-cycle path. Okay, so timing exceptions are nothing but the false path. Okay, false path, and then the multi-cycle path, false path and multi-cycle path. Okay, so what we will be covering is we'll be covering how it is taken care in stacked and what will happen in TDF time. So we'll be covering. Okay, false path and multi-cycle path are the timing exceptions. So we will cover how is it how it is taken care in stacked and what will happen in TDF. All those things we will try to cover. Okay, so how it is taken care in stacked, how it is how it is taken care in taken care in stacked. Okay, and then what will happen in TDF. Okay, what will what will happen in TDF. Okay, so all those things we will be covering. Okay, so timing exceptions are nothing but the false path and multi-cycle path. Okay, so like how it is taken care in stacked, what will happen in TDF, all those things we will be covering. Okay, so these are some of the main important topics which is there in the ATPG course. So ATPG, it's a very vast topic, so and it's also not a very straightforward topic. So like it will be we will be taking around 10 to 12 sessions in order to cover this ATPG topic. Okay, and the next topic is simulations. Simulations, it is actually to validate, it is to validate the patterns which was generated during ATPG. So which means before delivering the patterns. Okay, so before delivering the patterns, delivering the patterns, before delivering the patterns generated during ATPG, generated during ATPG. Okay, before delivering the patterns generated during ATPG to test the chip after manufacturing. Okay, to test the chip after manufacturing. Okay, after manufacturing, we need to validate once whether proper patterns are generated or not. Okay, we need to validate once whether proper patterns are generated or not. We need to validate once whether proper patterns are generated or not. Whether proper patterns are generated or not. So that is what is called as simulation. Okay. So before delivering the patterns generated during ATPG to test the chip after manufacturing, we need to validate once whether proper patterns are generated or not. So that is what is called as simulation. So it is to validate the patterns which was generated during ATPG. Okay, before delivering the patterns generated during ATPG to test the chip after manufacturing, we need to validate once whether proper patterns are generated or not. So that is what is called as simulations. Okay. So simulations, what we will be doing is we will be covering the theory as well as practicals. We will be covering it simultaneously. Okay. The theory and practicals, it will be done simultaneously. The theory and practical will be doing it simultaneously. Okay. So yeah, that is how simulation topic will be covered. So the theory and the practicals, it will be covered simultaneously. Okay. So what are all those topics? What are the syllabus? What is the syllabus of our simulation topic? We will try to understand. So simulation, first we will try to understand what is simulation, what exactly happens in simulation. Okay, what exactly happens in simulation, and then like what is the need of simulation, what is the need of simulation, what is the flow of simulation. Okay, what is the flow of simulation, and we will be covering like serial simulations and parallel simulations. So what is serial simulation, what is parallel simulation, why do we require serial and parallel simulations? So we'll be covering that. So we'll be covering the serial and parallel simulations. We will cover serial and parallel simulations, we will be covering. Okay, serial and parallel simulations. And then we will be understanding how to analyze the waveforms. Okay, how to analyze the waveforms we will cover. So analyzing the waveforms, how to analyze the waveforms in the simulation environment, we will try to observe. And then we will also cover like simulation mismatch debug. So if suppose your simulation fails, so how to debug it, so that also we will cover. So simulation mismatch debug, so if in case your simulation fails, what is the procedure to debug the simulation mismatches, we will be covering it in our course. Okay. And then these are all the topics which is there in our syllabus, like what is simulation, what is the need of simulation, what is the flow, serial and parallel simulation, observing the waveforms, and simulation mismatch debug procedure are all a part of our syllabus. So I will be additionally taking few more extra topics, one more like two more extra topics in simulation. So I will be covering two more extra topics. So which is nothing but we will be discussing about this scenario. So serial simulation, so scenarios that will cause, okay, scenarios that will cause serial simulation pass and parallel simulation fail. Parallel simulation fail, okay, and scenarios which will cause serial simulation fail and parallel simulation pass. Parallel simulation pass. So what kind of scenarios it will cause like this? So that is one extra topic we shall be covering. So scenarios that will cause serial simulation to pass and parallel simulation to fail, and what scenario will cause serial simulation to fail and parallel simulation to pass. Okay, so that is what I will be discussing as an extra topic. Okay. And in our course, as of now, in simulation, only no timing simulation is covered. So as of now, only no timing simulation is covered. So as of now, in our course, only no timing simulation is covered. Only no timing simulation is covered in our course. Okay, so as of now, in our course, only no timing simulation is covered. Okay, so yeah, this is what is the simulation topic. And the next one is this JTAG. So next topic is JTAG. So JTAG stands for Joint Test Action Group. So this is the full form of JTAG. So JTAG stands for Joint Test Action Group. So it is actually a IEEE 1149.1 standard. Okay, so JTAG stands for Joint Test Action Group. So it is actually an IEEE 1149.1 standard. Okay, so what is the need of JTAG? What is the need of JTAG? So one need of JTAG is actually to minimize the number of ports from top level, and the other one is to achieve boundary scan. Okay, JTAG, the full form of JTAG is Joint Test Action Group. So it's a IEEE 1149.1 standard. So need of JTAG is actually to minimize the number of ports from top level and also to achieve boundary scan. So these are the needs of JTAG. Okay, so now let us first try to understand this point. So how if we go for JTAG, we are able to minimize the number of ports from top level. How? We will try to understand it in the next slide. Okay, so here in this case, if you see, here I have kept a list of some important signal like memory bypass enable, EDT bypass enable, int mode, Intel test enable, X to mode, L test, Xtel test enable. Like that, I have kept a list of some important signals. Okay, so these are just a list of some important signals. Okay, so these are whatever I have listed here. So these are just a list of some important signals. These are just a list of some important signals. These are just a list of some important signals. Okay, important signals. There will be many more signals like these. Okay, there will be many more signals like these. Many more signals like these. Many more signals like these. Okay, so here I've kept a list of some important signals like memory bypass enable, EDT bypass enable, int mode, Intel test enable, X mode, Xtel test enable. Like that, I have kept a list of some important signals. So these are just a list of some important signals. There will be many more signals like these. Now, if all these signals are to be controlled from the top level, okay, if all these signals are to be controlled from the top level, okay, if all these signals are to be controlled from the top level, if all these signals are to be controlled from top level, okay, like this. So if you allocate a top level port in order to control this memory bypass enable, you are allocating one top level port to control this EDT bypass enable, you are allocating a top level port to control this int mode, one top level port for that Intel test enable, one for that X mode, one for that Xtel test enable, and so on. If you keep on, so as I told, these are just a list of some important signals. There will be many more signals like this. Now, if all these signals are to be controlled from the top level, so if you allocate a top level port in order to control each and every signal, like you're allocating a top level port to control memory bypass enable, one top level port for EDT bypass enable, one for int mode, one for Intel test enable, like that. If you allocate a top level port in order to control each and every signal, then what will happen? The number of top level ports will increase drastically. So if all these signals are to be controlled from top level, what will happen? Number of top level ports will increase drastically. Okay, what will happen? Number of top level ports. Number of top level ports will increase drastically. Will increase drastically. Number of top level ports will increase drastically. Okay. So if all these signals are to be controlled from the top level, then what will happen? The number of top level ports will increase drastically. Okay. So that is why we will be making use of JTAG to internally control the static signals. Okay. So we use JTAG. So we use JTAG to internally control the static signals. To internally control the static signals. Internally control the static signals. Okay, we will be making use of JTAG in order to internally control the static signals. Okay, so here I have kept a list of some important signals. These are just a list of some important signals alone. There will be many more signals like these. Now, if all these signals are to be controlled from the top level, which means you allocate a top level port to control that memory bypass enable, one for EDT bypass enable, one for int mode, Intel test enable, like that. For each and every signal, if you allocate a top level port in order to control each and every signal. So if all these signals are to be controlled from top level, then what will happen? Number of top level ports will increase drastically. Number of top level ports will increase drastically. So we use JTAG to internally control the static signals. Okay, so that is why you will be making use of JTAG to internally control the static signals. Okay, so this is how we will be using JTAG in order to minimize the number of ports from the top level. Okay, so when we cover this topic, what are the topics we'll be covering as a part of our JTAG training is, we will be covering the need of JTAG. Okay, we will be covering the need of JTAG. Need of JTAG we will cover, and then we will be covering the difference between the static signals and dynamic signals. Okay, we will be covering the difference between static and dynamic signals. We'll be covering the difference between static and dynamic signals. Static and dynamic signals. Okay, so we will be covering the difference between static and dynamic signals. Okay, so here we have told, right, we will be making use of JTAG to internally control static signals. So we'll try to understand what is the difference between static and dynamic signals with the help of some examples we will try to understand. Okay, and then we will be understanding about the JTAG tap architecture. We will be understanding about the JTAG tap architecture. Okay, we will be understanding about the JTAG tap architecture, and then we will be understanding about the JTAG controller. We will be understanding about the JTAG controller. So JTAG controller is actually a 16-state FSM. So JTAG controller is a 16-state FSM. So we will be like understanding about the JTAG controller, the 16-state FSM. We will be understanding about each and every state which is present in that FSM. We will be understanding that. So while we are understanding this JTAG controller, that is why we are understanding the various states which is there in the 16-state FSM, we will also simultaneously explore how with the help of JTAG we are able to internally control the static signals. So while we are understanding the various states of the JTAG FSM, we will simultaneously explore how with the help of JTAG we are able to internally control the static signals. Okay, we will simultaneously understand. Okay, we will simultaneously understand, simultaneously explore, okay, simultaneously explore how with the help of JTAG, how with the help of JTAG, okay, with the help of JTAG, okay, so we will simultaneously explore how with the help of JTAG we are able to internally control the static signals. So how with the help of JTAG we are able to internally control the static signals, internally control the static signals. Okay, so we will understand it. Okay, we will simultaneously understand this. Okay, so we will be understanding the JTAG controller. So JTAG controller will be a 16-state FSM. Okay, JTAG controller is actually a 16-state FSM. We'll be understanding the various states which is there in the 16-state FSM. So while understanding the various states of the 16-state FSM, we will simultaneously explore how with the help of JTAG we are able to internally control the static signals. Okay, and then yeah, we will also be understanding IEEE 1687 standard, IEEE 1687 standard, IJTAG we will be understanding. So as I told, I have not included it in the demo session because in order to give an overview about IJTAG, you have to understand JTAG completely, but you do not know JTAG as of now, right? So that's why I did not include it in the demo session, but we will be covering this in our regular course. So we'll be covering the IEEE 1687 standard, which is IJTAG. So we will be understanding the architecture of this IEEE 1687 standard. So what is the architecture? We'll try to understand, and we will see. We will have a comparison between JTAG and IJTAG. Okay, we will have a comparison between JTAG and IJTAG. Okay, we will see. We will have a comparison between JTAG and IJTAG. We will have a comparison. Okay, and then we will also see what is the advantage of IJTAG. We will also see what is the advantage of IJTAG. We will also see what is the advantage of IJTAG. Okay, so in JTAG, we'll be covering what is the need of JTAG, what is the difference between static and dynamic signals, the JTAG tap architecture, JTAG controller, which is actually a 16-state FSM. So while understanding the various states in the 16-state FSM, we will simultaneously explore how with the help of JTAG we are able to internally control the static signals. We will understand that. And we will also be covering the IEEE 1687 standard, which is IJTAG. So we'll see the architecture of that 1687 standard, and we'll do a comparison between JTAG and IJTAG, and we'll also try to understand what is the advantage of IJTAG. Okay, and next what we will do is, so now need of JTAG, it is also to achieve boundary scan, it is written, right? So what is this boundary scan? We will try to understand here. Okay, so boundary scan, so here in this case, chip 1, chip 2, chip 3 are properly passing the test of DFT, but still the board is failing. Okay, so chip 1, chip 2, chip 3 are properly passing the test of DFT, but still the board is failing. So what is written here in this slide, we will try to understand. So first what will happen is, first chips will be manufactured. So first what will happen? Chips will be manufactured. Okay, so first chips will be manufactured. Okay, so first what will happen? First chips will be manufactured. Okay, first chips will be manufactured. After that, what will happen? Chips will be tested on ATE. ATE, or we call it as a tester. Okay, chips will be tested on ATE. ATE, we also call it as a tester. Okay, so chips will be tested on ATE. We also call it as a tester. Okay, so you'll be having the ATE like this. So this is the ATE. Okay, this is the ATE, and then here you have like this. This is nothing but chip 1, this is chip 2, okay, and then this is chip 3. So in our case, 3 chips are considered, right? Chip 1, chip 2, chip 3. So input of the chip will be connected to the AT, output of the chip will be going back again to the AT. Like this, input of the chip will be connected to the AT, output will be going back again to the AT. So this is how it will be there. So chips will be tested on ATE or tester like this. Chip 1, chip 2, chip 3, it is there. So input of the chip will be connected to the AT, output of the chip will be going back again to the AT. So in this case, suppose chip 1, chip 2, chip 3, they have passed their test on AT. So chip 1, chip 2, chip 3, they have passed their test on AT. They have passed their test. They have passed their test on AT. They have passed their test on AT. So which means output of the chip is equal to expected output, as we already discussed in the initial slide. So chip 1, chip 2, chip 3, they have passed their test on AT. They have passed their test on AT. So which means output of chip will be equal to the expected output, as we already discussed it in the first initial starting slides. Okay, pass the test on AT means output of chip will be equal to the expected output. Output of chip will be equal to the expected output. So chip 1, chip 2, chip 3, they have passed their test on the AT. Output of the chip is equal to the expected output. It means that chip 1, chip 2, chip 3, they are not having any manufacturing defects. So it means that chip 1, chip 2, chip 3, they are not having any manufacturing defects. They are not having any manufacturing defects. Okay, they are not having any manufacturing defects. So chip 1, chip 2, chip 3, they have passed their test on AT, right? So which means they are not having any manufacturing defects. Okay, chip 1, chip 2, chip 3, they are not having any manufacturing defects. Okay. Now, what will happen? Now, these chips are placed on the board. So next, what is happening? These chips are placed on the PCB board. Okay, chips will be placed on the PCB board. Chips are placed on PCB board. So chips are placed on PCB board like this. So this is your PCB board. Okay, so this is your PCB board. Okay, and then what will happen? This is nothing but chip 1, chip 2, chip 3. So chips are placed on the PCB board. So this is nothing but chip 1, chip 2, chip 3. Okay, and then the interconnection between the chips are also there. So the interconnection between the chips are also there. Okay, the chips are placed on PCB board, and then the interconnection between the chips are formed. So chips are placed on the PCB board and interconnection between the chips are actually formed. And after this, what is happening? Board is tested. After this, what is happening? Board is tested. Board is tested. And when the board is tested, what is happening? It is failing. It is failing. Why when the board is being tested, it is failing? So chip 1, chip 2, chip 3, they are internally not having any manufacturing defect because they have already passed their test on AT. Okay, so chip 1, chip 2, chip 3. Chip 1, chip 2, chip 3, they are internally not having any manufacturing defects. They are internally not having any manufacturing defects. We are internally not having any manufacturing defects. So chip 1, chip 2, chip 3, they are internally not having any manufacturing defects. Okay, they are internally not having any manufacturing defects. Why? Because they have already passed their test on AT. Okay, as they have already passed passed the test on AT. Okay, because they have already passed the test on AT. Already passed the test on AT. Okay, chip 1, chip 2, chip 3, they are internally not having any manufacturing defects because they have already passed the test on AT. Okay, because they are already passed the test on AT. But why is the board failing now? But why is the board failing? So this can be due to the manufacturing defects in the interconnection between the chips. So why is the board failing now? So this can be due to the manufacturing defects in the interconnection between the chips. Okay, so this can be due to the manufacturing defects in the interconnection between the chips, in the interconnection between the two chips. Okay, when the board is being tested, it is failing. Why is it failing? So this can be due to the manufacturing defects in the interconnection between the two chips. Okay, due to the manufacturing defects in the interconnection between the two chips. Okay, so we actually go for boundary scan in order to test the interconnection between the two chips. Okay, we go for boundary scan in order to test the interconnection between two chips. Okay, so this is to test the interconnection. So this is to test the interconnection between two chips. Between two chips. Okay, we go for boundary scan in order to test the interconnection between two chips. Okay, we'll be going for boundary scan to test the interconnection between two chips. Okay, so what are the topics which we'll be covering it as a part of our boundary scan topic is? So what are the subtopics we will be covering it as a part of this topic is? So we will be covering the boundary scan cell structure. What is the structure of a boundary scan cell we will be covering? Okay, we'll be covering the boundary scan cell structure we will be covering. Okay, and we will also be covering the modes of operation of boundary scan cell. Okay, what are the modes of operation? Modes of operation of boundary scan cell. Modes of operation of boundary scan cell. Okay, modes of operation of boundary scan cell. And we will also be covering the various instructions like X test instruction. We'll be covering the X test instruction, the mandatory instructions of JTAG. We'll be covering X test instruction, sample preload instruction, bypass instruction, all those things we'll be covering. Sample preload. Okay, so like sample preload instruction, and then like bypass instruction, all those things we will be covering. So the X test instruction, sample preload instruction, bypass instruction. So these are the mandatory instructions of JTAG. So we'll be covering all those instructions. So when we discuss about this X test instruction and sample preload instruction, okay, when we discuss about this X test and sample preload instruction, we will simultaneously understand how with the help of JTAG you are able to achieve boundary scan. So when we discuss about that X test instruction, sample preload instruction, all those things when we discuss, at that time you will be able to understand how with the help of JTAG you are able to achieve boundary scan. Okay, so these are all the topics which we will be covering it as a part of our boundary scan course. Okay, so when we cover this X test sample preload instruction and all, you'll be able to understand how with the help of JTAG you are able to achieve boundary scan. Okay, and yeah, next one is memory built-in self-test. So as its name suggests, we use MBIS techniques in order to test the memories. So memory built-in self-test. So as its name suggests, we will be making use of MBIS technique in order to test the memories. So as a part of this MBIS course, what are the topics we'll be covering is, we will be covering the basics of memories. We'll be covering the basics of memories, not very much in detail. So we will be like covering like what are the types of memories, RAM and ROM, SRAM and DRAM. So those things we'll just see an overview about those things. Okay, that is nothing but the basics of memories we'll cover. And then we will go ahead with the topics which is required for a DFT engineer. So which is nothing but the memory fault models. Okay, we will be covering the various memory fault models. Okay, so there will be various memory fault models like stuck at fault model, transition fault model, and then address decoder fault, and then like coupling fault. Like that, there will be various fault models: stuck at, transition, address decoder, coupling. Okay, so there will be various fault models in memory. So we'll be covering those fault models. Okay, stuck at fault model, transition fault model, address decoder fault, and coupling fault. We'll be covering that. Okay, and then Memories, they will be tested using generalized algorithms. Okay. So memories, they will be tested using generalized algorithms. Memories are tested using generalized algorithm. Okay, memories are tested using generalized algorithm. Okay, generalized algorithm. Okay, so we will be covering some algorithms. We will be covering some algorithms, some basic algorithms, like 0 1 algorithm. Okay, 0 1 algorithm, and then checkerboard algorithm. Okay, we'll be covering the 0 1 algorithm and then checkerboard algorithm, and then we'll be covering these algorithms like maths algorithm, maths plus algorithm, and then maths plus algorithm. Okay, and then like March X algorithm. Okay, so March X algorithm, March C algorithm. So we'll be covering various algorithms. Okay, so memories will be tested using generalized algorithms. So some basic algorithms will be covering like 0 1 algorithm, checkerboard algorithm, maths plus, March X, March C, like that we'll be covering various algorithms. So in all these algorithms, we will be covering what is the sequence of those algorithms. So each algorithm, they will be having a specified sequence. Okay, each algorithm, they will be having a specific sequence. So what is the sequence of that particular algorithm? And then which algorithm will be able to cover which faults in memories and how, all those things we will understand. Okay, so which algorithm will be able to cover which faults in memories, all those things we will cover. Okay, so memories, they are actually tested using generalized algorithm. Like you'll be having these algorithms, some basic generalized algorithms we will understand in our course, like 0 1 checkerboard, maths plus, March X, March C and all. So for each and every algorithm, we will understand what is the sequence of that algorithm. So each algorithm, it will be having a specific sequence. Okay, it will be having a specific sequence. So what is the sequence of that algorithm, we will understand. And then we will try to understand which algorithm will be able to cover which faults in memories. Okay, which algorithm will be able to cover which faults in memories, we will be understanding that. Okay, and then why memories are tested using generalized algorithm and how memories are tested using generalized algorithm, you will be able to understand these 2 points when we do this. Okay, why memories are tested using generalized algorithm, how memories are tested using generalized algorithm, all those things you will be able to understand when we do this course. Okay, when we do the course, you'll be able to understand this. So why memories are tested using generalized algorithm and how memories are tested using generalized algorithm. That is what, while covering each and every algorithm, will be understanding the sequence, and also we will understand which algorithm will be able to cover which faults in memories and how we will be understanding, right? So at that time itself, we will be able to understand like how memories are tested using generalized algorithm and why memories are tested using generalized algorithm. We will discuss it during our course. Okay, and after that we will be covering the Tessent embist. We will be covering the Tessent embist. So Tessent embist means if you want to implement embist using Tessent tool, so that is what is called as Tessent embist. Implementing embist using Tessent tools is what is called as Tessent embist. So in Tessent embist, we will be covering the Tessent embist implementation and architecture. Okay, so if you want to so implementing embist using Tessent tools or achieving embist using Tessent tools is what is called as Tessent embist. So in Tessent embist topic, we will be covering like the Tessent embist implementation and architecture. Okay, we'll be covering the Tessent embist implementation and architecture. Okay, so Tessent embist implementation will be covering, and we will also cover the Tessent embist architecture. We will cover Tessent embist architecture. We will cover it, and then what we will cover? We will cover the Tessent embist operation protocol. We will cover the Tessent embist operation protocol. We will cover. Okay, Tessent embist operation protocol. We will cover it. So while understanding the Tessent embist operation protocol, so there will be various signals like this setup signal, mbist pg enable, like that there will be various signals. Okay, so this setup signal and then mbist pg enable signal, Okay, so MBIST PG enable signal. So MBIST PG enable signal, and then like go signal, done signal, like that you'll be having various signals. Go bit, done bit, like that you'll be having various signals. Okay, so we will be understanding about all these signals. So when we do the test and MBIST operation protocol, we'll be understanding about all these signals. So what is a BIST setup signal? What is a MBIST PG enable signal? What is a go signal? What is a done signal? All those things we will understand. And we'll also try to understand the concept of grouping of memories. So group concept and then step concept we will understand. So what is group concept? What is step concept? All those things we will understand it in MBIST. Okay, so by the end of this topic, once we complete the test and MBIST, you will be able to understand why it is called as built-in self-test. Why it is called as self-test, you will be able to understand. But after completion of this topic, after completion of the MBIST topic, you will be able to understand why is it called as built-in self-test. Why self-test? Okay, you will be able to understand. So once we complete the test and MBIST architecture fully, you will be able to understand why it is called as built-in self-test. Why self-test? You'll be able to understand after completion of this MBIST architecture. Once we do the test and MBIST architecture, you'll be able to understand that. Okay, why it is called as self-test. Okay, so now whatever I have told, it was from theory side. So in theory side, these are all the topics which we will be covering. Okay, so in theory side, these are all the topics which we will be covering. Okay, so in labs, what are the topics we will be covering? We will try to understand. So in labs, we will be covering IJTAG and then MBIST and then scan insertion. We'll be covering both top-down as well as hierarchical approach we will cover. And then EDT and OCC insertion we will be covering. And then ATPG pattern generation, ATPG and MBIST simulations. So all those things we will be covering. Boundary scan, it is covered only theoretically. So boundary scan, it will be covered only theoretically, because I think we don't have the license for doing the boundary scan. Okay, for doing boundary scan, I think we don't have the license. So that's why boundary scan, it will be covered only theoretically. So yeah, boundary scan only, it will be covered only theoretically. And these are all the topics which will be covered in the lab. So IJTAG, MBIST, scan insertion. So basically in scan insertion, there are two approaches, like top-down approach as well as hierarchical approach. So we'll be covering both these approaches. And then EDT and OCC insertion, ATPG pattern generation, ATPG and MBIST simulations. So we will be covering all these topics here. Okay. So basically in labs, our labs are actually divided into 4 levels. So level 1, level 2, level 3, level 4, like this. Our labs are actually divided into 4 levels. Okay, our labs are divided into 4 levels. So level 1, level 2, level 3, level 4. So like that, our labs are actually divided into 4 levels. Okay, so just one second. Yeah, my PPT had got hacked. Okay. So our labs are actually divided into 4 levels: level 1, level 2, level 3, and level 4. So level 1 and level 2 projects, they are actually like simple test cases. Okay, so this level 1 and level 2 projects, they are actually like simple test cases, simple labs. So complexity will be less, like maximum number of flops will be around 100 to 200 flops. So this level 1 and level 2 projects, so these will be like simple labs. So this level 1 and level 2 projects, these are simple labs. So like the complexity would be less. Okay, so the complexity will be less. Okay, so complexity will be less. Complexity will be less. So which means like the maximum flops. So maximum number of flops. Maximum number of flops will be like around 100 to 200 flops. 100 to 200. Maximum of some 100 to 200 flops will be there. Okay, so this is what these are simple labs. These are simple labs. Complexity will be less. So maximum of 100 to 200 flops will be there. Okay, so this is for the level 1 and level 2 projects. Level 3 and level 4 projects. So these are the labs with higher complexity. So these are the designs with higher complexity. So level 3 and level 4 projects, these are the designs with higher complexities. Okay, level 3 and level 4 projects are the designs with higher complexity. Okay, designs with higher complexity. Okay, so you will be having complexity. Okay, so you will be having around like in level 3 projects, you will be having around 4k flops. Okay, you will be having around 4K flops in level 3 projects, and in level 4 projects you will be having around 44K flops. You will be having around 44K flops. So level 3 projects you will be having around 4K flops. Level 4 projects you will be having around 44K flops. Okay, so these are the designs with higher complexities. So this level 3 and level 4 projects you can add it up as a, you can like project it as a project work in your resume. So you can project this. So you can project the level 3 and level 4 projects. So you can project it as a project work. You can project it as a project work in your resume. Okay, so this can be a project work in your resume for this course. Okay, so level 3 projects you will be having around 4K flops. Level 4 projects you will be having around 44K flops. So these are the designs with higher complexity. So you can write it as a project work in your resume. Okay, so now first coming to this level 1 and level 2 projects. So level 1 and level 2 projects you will be having 11 test cases. So for this 11 test cases in level 1 projects, we are going to perform the scan insertions. Okay, so for the 11 test cases, we are going to perform the scan insertions. Among these 11 test cases also, two test cases will actually be to familiarize yourself with the flow. Okay, two test cases will be there to familiarize with the flow. Okay, so which means like if you are going to implement scan insertions using mentor graphics tool. So what is scan insertion? Replace all the normal flop with scan flops and do the scan chain stitching. So if you have to do the scan insertion using mentor graphics tools, means then there will be a set of steps or a procedure that you need to follow. So that is what is called as the flow of scan insertion. Okay, so what is scan insertion? Normal flops will be replaced with scan flops and scan chains will be stitched. So now if you want to implement it using mentor graphics tools, then you will be having a set of steps or a set of procedure to do that. There will be a procedure and there will be a list of steps which you need to follow for doing it. So that is what is called as the flow of scan insertion. So two test cases you will be having in order to familiarize yourself with the flow. Okay, in order to familiarize yourself with the flow, you will be having two test cases. Okay, so and also to understand to what is it, familiarize yourself with the flow, familiarize yourself with the tool environment. So you'll be making use of Tessen tools. So how is the Tessen tool environment? What are the commands, various commands which is used in the Tessen tool environment? And then how the schematic of a Tessen tool environment will look like, how we can trace some logic in the schematic, or else how we can analyze certain violation in the schematic. Like that you'll be having some, in order just to get a idea about the tool environment, about the commands, about the schematic, and also about the flow. That is, in order to achieve scan insertion is you need to follow certain steps, or you need to follow a procedure would be there. So what is that procedure? In order to familiarize yourself with that, so for that reason, first some two test cases will be there. So the two test cases will be to familiarize yourself with the flow and the tool environment. Okay, the remaining 9 test cases, so the remaining 9 test cases, we will be having the DRC violations. So in the remaining 9 test cases, you will be having the DRC violations. Some DRC violations will be there. Okay, so in the remaining 9 test cases, you will be having some DRC violations. Okay, so I had actually told, right, there will be like various scan DRCs I had told, right, like while telling the theory part itself, I had told, right, like clock controllability, set reset controllability, potential raise, bus contention, like that I had listed out some DRCs, right, scan DRCs. So in each and every test case, you will be having some DRC violations. Okay, you will be having some DRC violations, and we will be fixing the DRC violations. We will be solving those DRC violations. And in order to resolve the DRC violations while in mentor graphics tools, we are basically having 3 methods. So you will be having 3 methods to fix the DRC violation. So one method is nothing but the manual editing of netlist method. So one method of fixing the DRC is manual editing of netlist. So one method is manual editing of netlist method. Okay, so one method will be to manually edit the netlist and fix the DRC. So that is one method. Another method is you can actually fix the DRC using the set of commands like create instance, delete connection, okay, delete connection, create connection. Like that, there will be some set of commands with the help of which you can actually add the logic to fix the DRC violation. Or else you can also go for this auto fix method. So in auto fix method, what will happen is the tool itself will automatically add the logic in order to resolve the violations. Okay, so we will try to understand how we can fix the DRC violation using all these three methods, that is manual editing or netlist method, or is using that create instance, delete connection, create correction method, or is using this auto fix method. How you can actually fix the DRC violations, we will try to understand. Okay, and we will also try to understand like among these three methods which one is widely preferred and why it is widely preferred. We will compare all these three methods of fixing the DRC violation. We will have a comparison on it, and we will try to understand like which one is more preferred and why it is more preferred. We will try to understand, okay, which one is more preferred and why is it more preferred. You will be able to understand that. Okay, and we will also be understanding the various reports and outputs of scan insertion. We will also understand about the various reports and outputs of scan insertion. We will also understand about the various reports and outputs of scan insertion. Okay, so what are the reports and outputs which is generated during the scan insertion run? We will try to understand that, and yeah, we'll try to see what are the contents and what is available in that reports and outputs of scan insertion. We'll try to understand all those things. Okay, and in level 2 projects, what we are going to do for the same 11 test cases, we are going to perform EDT insertions, ATPG, and simulation. So scan compression is also called as EDT insertion only. So we'll be doing the EDT insertion, ATPG, and simulations. So in EDT labs, what we will be doing is we will be inserting EDT logic. Okay, we'll be inserting the EDT logic. Okay, and we will be like analyzing the EDT logic in the schematic. Okay, whatever logic has been inserted, right, we'll be analyzing the EDT logic. We'll be analyzing the EDT logic in schematic. We'll be analyzing the EDT logic in schematic, and we will also understand about the understanding the output files of EDT run. We'll be understanding the output files of EDT run. Okay, we'll be understanding the output files of EDT run. Okay, so in EDT labs, we'll be understanding again flow also. What is the flow of EDT insertion? We'll be understanding. Okay, so how we will be inserting the EDT logic in the schematic, we will understand. So how to analyze the EDT logic in the schematic, we will understand, and we'll also understand the various output files of EDT run. So all those things we will understand. Again, in ATPG also, we will be understanding what is the flow of ATPG, and in ATPG we will be practicals will be doing it for these fault models. So stuck at fault model, transition delay fault model, and IDDQ fault model. So we will be doing the pattern generation. So we'll be doing the pattern generation for these fault models. So for stuck at fault model, transition delay fault model, and for this IDDQ fault model, we will be doing the pattern generation in our labs. And in our ATPG topic, our main goal in labs, is to focus on coverage analysis and coverage improvement. Okay, coverage analysis and coverage improvement. So this is what we will be mainly focusing in our lab. So we will be mainly focusing on coverage analysis and coverage improvement in our labs. Okay, and then we will also understand like generating patterns. So pattern generation with TDT and bypass pattern, all those things we will understand. So pattern generation with TDT, and then bypass pattern generation, all those things we will understand. Okay, so pattern generation with TDT, bypass pattern generation, all those things we will understand. So that is what we are going to understand it in our ATPG lab. So we will understand the flow, and then we will be doing the pattern generation for these three fault models in our lab, stuck at, TDF, and IDDQ. And we will mainly be focusing on coverage analysis and coverage improvement portion. We will also be working on pattern generation with EDT, bypass pattern generation, all those things also we will be covering. Okay, and then simulation, as I told, the theoretical concept of simulation, we will be covering it by practically demonstrating in the lab. So as I already told, right, these topics, what are the topics I had told at the time of theory time, that is what will be covered. So simulation, as I already told, we will be theory and practicals, we will be doing it simultaneously. Okay, so we will be understanding the concept of simulation by practically demonstrating in the lab. So theory and practical will be done simultaneously. So all these things only will be doing. So the flow of simulation, serial and parallel simulation, analyzing the waveform, simulation mismatch, debug. So all those things we will be covering it as a labs in our practicals of our simulation topic. Okay, so this is what. And for simulation, as of now, only no timing simulation is covered. Okay, yeah. And yeah, this is what is regarding the level 1 and level 2 projects. Now, level 3 and level 4 projects. Level 3 and level 4 projects, what do they do? So, level 3 and level 4 projects, they will be covering the entire flow. So, if you see in level 1 and level 2 projects, we have not done the IG tag insertion, MBIST insertion, OCC insertion, all those things sorry, all those things we have not covered it in our level 1 and level 2 projects. Okay, IJ tag insertion, MVistor, and then that OCC insertion, all those things are not covered in the level 1 and level 2 projects, but all those things we will be doing it in our level 3 and level 4 projects. So in our level 3 and level 4 projects, we'll be covering the entire flow. That is, we'll be doing the IJ tag insertions, MBIST insertions, and then EDT, OCC insertions, EDT and OCC insertions, and then we'll be performing the synthesis, and then we will be doing the scan, and then we'll be doing ATPG, and then we'll be doing the simulations. So this is what is our complete flow. Level 3 and level 4 projects, we will be covering the entire flow. So in level 1 and level 2, if you see IJ tag, MBIST, OCC, all those things were not done in the labs, right? But in level 3 and level 4 projects, we'll be doing the entire thing. So we'll be doing the IJ tag and MBIST insertion, EDT, OCC insertion, synthesis, scan, ATPG, simulation, the complete flow, we will be covering it in the level 3 and level 4 projects. Okay. So level 3 and level 4 projects, that is what, as I already told you, in level 3 projects, you will be having around 4K flops. Level 4 projects, you will be having around 44K flops. So these are only the designs with higher complexity. The level 3 and level 4 projects are the designs with higher complexity. So it will be, you can write it as a project work in your resume. So you can write this level 3 and level 4 project as a project work in your resume. Okay. And then in this level 3 projects, like level 3 projects is actually a hierarchical scan approach, right? So if it is hierarchical scan, means some more extra concepts will also be covered at this time. So while we are doing the level 3 projects, we'll be understanding the hierarchical scan approach. So some more theoretical topics will also be covered when we do the level 3 projects. So what are the theoretical topics? So theoretical topics like scan wrappers, what are scan wrappers, and then the concept of in-test, concept of in-test, concept of X-test, and concept of pattern retargeting. Okay, concept of pattern retargeting. All these things will be covered. Okay, targeting. Okay, all these things will be covered. Okay, so in level 3 projects, it is nothing but the hierarchical scan approach. So in level 3 projects, it is hierarchical scan approach. So like some more theoretical topics will also be covered while we are doing the level 3 projects, like scan wrappers, concept of in-test, concept of X-test, concept of pattern retargeting. So all those things will be covered when we do the hierarchical scan approach. Okay, so yeah, this is what. So this is what is the summary of what will be covered in our labs. So basically, like this course, what will happen is, so this course will be for around 5.5 months. This entire course will be for around 5.5 months. Okay, the course will be from 5.5 months to 6 months will be the course duration. Okay, so the initial 2 to 2.5 months, the initial 2 to 2.5 months, basic sessions will be covered. Okay, the basics will be covered for the initial 2 to 2.5 months. So in basics, we will be covering GVim, okay, and then Linux, and then Tickle, and then digital design. Okay, so digital design, and then CMOS, Verilog. So all those things will be covered as a part of basic training. Okay, so as a part of basics training, we'll be covering GVim, Linux, Tickle, digital design, CMOS, Verilog. So all those things will be covered as a part of basics training. Okay, so now after completing the basics training, the next 3.5 months to 4 months. Okay, so the next 3.5 months to 4 months, okay, next 3.5 months to 4 months, we will be covering the DFT advanced course. Okay, we will be covering the DFT advanced course. Okay, so in the DFT advanced course, whatever we had discussed in the previous slides, so that is what will be covered, whatever I had discussed. So the course content both for theory as well as for labs I had given in the previous slide, right? So that is whatever we had discussed in the previous slides will be covered. Okay, so whatever was discussed in previous slides. So whatever was discussed in previous slides will be covered. So I had given the entire course syllabus as well as what will be covered in the theory and lab I had told, right? So that is whatever we had seen in the previous slides. So that is what will be covered in the DFT advanced course. Okay. So apart from course syllabus, I will be covering some extra topics. Okay. So apart from course syllabus, I will be covering. So whatever topics I had told now was the part of the course syllabus. Apart from the course syllabus, I will be covering the extra topics. Okay. So I will be giving you an overview about the extra topics, just an overview, not in detail. I'll just be giving you an overview about these extra topics. So what all the extra topics apart from course, what all the extra topics I will be covering it is. Okay, so I will be covering the IEEE 1500 standard. Okay, I'll be covering the IEEE 1500 standard, and I will be covering RAM sequential. I'll be covering ROM embist, and then I will also be covering logic based. I will also be covering logic based. Okay, so these extra topics I will just be giving you an overview. These are the topics apart from syllabus. Apart from syllabus, these are the extra topics which I will be covering, and I'll be giving you an overview about these topics like IEEE 1500 standard, RAM sequential, ROM, embed, logic bits, all these topics. Okay, and then I will also be covering static timing analysis STA. So static timing analysis, like it is actually not a DFT domain topic, but still some interviewers, they expect you to have some idea about the static timing analysis concepts. Okay, so like whatever is expected for a DFT interview. Okay, whatever is expected in DFT interview. Okay, whatever is expected in DFT interview will be covered. Okay, whatever is expected in DFT interview will be covered. Okay, so I will be covering that. So like what is setup time, what is hold time, what is setup violation, what is hold violation, which one is more critical, setup time or hold time, why it is more critical, how to find out the maximum frequency of operation of a circuit, like that. Some basic things, whatever is expected in a DFT interview will be covered. So STA is not a DFT topic, but some interviewers, they expect you to have a brief knowledge, some basic knowledge on STA. So whatever is expected in DFT interviews, I will be covering the STA concept as well. So these are the extra topics which I will be covering apart from the course. Okay. And yeah, in our course, what are the tools we will be using? So we will be, for MBIST, we'll be making use of Tessent MBIST. For scan, we'll be making use of Tessent scan. For EDT, we will be making use of Tessent test compress. For ATPG, we'll be making use of Tessent test compress. And for simulation, we'll be making use of QuestaSim. So these are all the tools which we will be making use for DFT in our course. Okay, for MBIST, we'll be using Tessent MBIST. For scan, we'll be using Tessent scan. For EDT, EDT and ATPG will use Tessent test compress, and for simulation, we'll be using QuestaSim. Okay, so these are all the tools which we will be using it in our course. Okay, and who can attend this course? Any student who is in final semester seeking DFT as their course curriculum, so you can attend the course. Or a new college graduate who is from relevant branches of engineering and science, you can also attend this course. So lecturers and professors who want to switch their career into real-time industry experience. So like you can also attend this course. So you're lecturer or professor, but now you want to switch to real-time work, means you can also attend this course. And working professionals from similar or other VLSI domains. So say for example, you're working in IT, but you now want to change your domain to VLSI, means you can attend this course. Or else like say for example, you're from physical design team, but now you want to shift to DFT team or something like that, then you can also attend this course. Okay, and then placement support. So we will be having tie-up with various VLSI companies. So like students are entitled to placement support based on the performance in their course activities. Based on the performance in their course assignments. So during the course, we will be giving you some assignments, tests, mock interview, presentation sessions, like that we will be conducting various activities. So based on your performance on those activities, you will be like given the placement opportunities. Okay, so students are entitled to placement support based on the performance in the course activities. So like we'll be conducting like assignments, and then the tests, we'll be conducting mock interviews, so and then some presentation session, and within the class during the session itself we will be like conducting some quizzes. So like that we'll be giving some various activities. So based on your performance on those activities, you will be given the placement support. Okay, and then mock interviews will also be conducted so that you will be able to face the real interview with confidence. Okay, mock interviews will also be conducted so that you will also face your original interview with confidence. Okay, so previous company interview questions and preparations. So what are the in previous companies, so some students would have faced the application oriented interview questions, like those kind of interview questions for each topic. So what are the application oriented interview questions was faced by the previous batch students, okay, in their interview. So I have collected a list of those application oriented interview questions. So I will be discussing that in our course, so like that for each topic. So let me just check if I'm having it here. So I'm having it in my other device. I'll just check if I'm having here. So just to show you, so scan difficult interview question, yeah, like this is for scan topic. So these are all the application oriented interview questions which the previous batch of students had faced in their interviews. So I will like we will be I've collected a list of those questions as well, and I've also written the answers. So I will be discussing all these things also in our course. So for each and every topic. So now I'm just showing it for the scan topic. Just like I'm having for the scan topic, for each and every topic, I have collected a list of application oriented interview questions which previous batches students have faced. So we will be covering the question as well as answer. We will be training you with that so that you will be able to know how to tackle if you get similar kind of questions, if you get similar kind of questions in your interview, how to tackle them, you will be able to have an idea about it. So that is why I have collected a list of application oriented interview questions which was asked in the previous batch students. So I have collected a list of those questions along with the answers. I have written it, and I will be discussing that in the course as well. Okay. So previous company interview questions and preparations. So that is what we will be doing. Okay. And yeah, that's it for the demo. So if you have now, let me just check the chat box. I wasn't able to check the chat box because while I'm presenting, chat box will not be visible. So let me just check the chat box. And if you have any other questions in that, you can ask. Okay. So let me see the chat box. So are you a fresher or working? So like I am having like around 20 batches of training experience for DFT domain. Okay, so for DFT course, I have around 20 batches of 20 batches of training experience for training the DFT domain syllabus. And then like I have also handled corporate trainings, like for 6 months corporate trainings for the same syllabus, for corporate trainings for Dell, and then for Intel, I have Intel Malaysia candidates. I have done corporate trainings for them, and I have also trained freshers as well as 1 or 2 year experience candidates from Juntron company as well. Okay, and I've also conducted some week-long workshops for college freshers as well as for corporates like L&T. I have given week-long workshops. Okay, so this is what is my experience. Okay. Can you cover from basics flip-flop counters? Yes, it will be covered. So first during this 2.2 to 2.5 months course of basic sessions. So digital design is a part of those basic training. So at that time, all the combinational and then the sequential logics will be covered. So in the first initial 2 to 2.5 months of course, so the digital design, you'll be having the digital design portion will be there. So there the combinational as well as sequential logic will be covered. Okay. Um, so will you be teaching course both basics and advanced? Okay. So like basics I will not be handling. So this basic courses, I will not be handling the basic courses. So DFT advanced course, I will be handling for some batches, theory and labs. I will be handling for the online batches. For offline batches, separate trainers will be handling that. Okay. So basics training, I will not be covering. Some other trainer will be covering that, all these basics. So for each topic, there will be a separate basic trainer to cover that. DFT advanced course, so I will be covering some batches, theory and lab, some batches, online batches I will be covering. Offline batches will be handled by the separate trainer. So many of them are saying no placement for freshers. So for like placement related queries, I will share with you Webhouse sir's number. So you can like check with Webhouse sir. So sir will be able to guide you on that. Okay. So sir will be able to give you a correct picture on like whether recently whether placements are happening properly or not. So how many students have got placed in the previous batches. So in order to get those details, like I will share with you Webhouse sir's number. So sir will be able to give you a correct picture on that. So let me just share sir's number. Just a second.
लास्टला भी दे नजराबाद वो मैप आपको
Okay, so I've shared Webhouse sir's number in the chat box. So you can contact Webhouse sir for queries related to placement. So sir will be able to give you a correct picture on that. Okay. I'm just checking if I've typed the number correctly. Just a second. Yeah, you can either contact Webhouse sir or else in the institute website you will be having a number, right? You can just contact that number for queries related to placements. Okay. Uh, yes, Priyatan, you can turn on your mic. Okay. Yes, Ramu, like while doing the course, we will be doing it in a slower pace. So this is a demo session. So we need to complete the overview of entire course within 3 hours. So it will be like a little higher pace. But when we do the regular course, it will be a slower pace. Okay. DFT advanced training timing. So like usually, so if it is for weekend, so timings will be like for weekend, you will be having like 9:15 to 12:15 will be the theory session. Okay, so this is on weekends. So 9:15 to 12:15, 9:15 a.m. to 12:15 p.m. So in the morning, you will be having the theory class. So you'll be having the theory class. Okay. So this theory class will be common for all. So common for all. Okay. And then afternoon 2 p.m. to 5 p.m. 2 p.m. to 5 p.m. or else 1:30 to 4:30. Okay, 1:30 p.m. to 4:30 p.m. based on like how they schedule it. Okay, 2 p.m. to 5 p.m. or 1:30 p.m. to 4:30 p.m. based on how they will be scheduling it. You will be having the labs. You will be having the labs. So this is only for weekend. Only for weekend enrolled students. Weekend enrolled students. Okay. And then during weekdays, you'll be having the labs. Okay, labs for weekday students will be there. Labs for weekdays enrolled students will be there. Okay, so labs for weekdays enrolled students will be there. So either in the morning or in the afternoon, either in the morning, that is 9:15 to 12:15 time slot, or in afternoon, or in the afternoon will be there. So that is from um, 2 p.m. to 5 p.m. time slot, or else 1:30 to 4:30 p.m. time slot. So based on how they will be allotted, so you will be having the labs during the weekdays. So this labs will be for the weekdays enrolled students. You'll be having the session either in the morning or else in the afternoon. It depends on how they will be scheduling it for the batch. So this is for the DFT advanced course. For basics, I'm not sure like how the sessions will be conducted, at what time the sessions will be conducted. I'm not sure for the basic student, for the basic classes. So you will be added up into a DFT group. So in the DFT group, they will be posting the schedules. Okay. So for 1 month, they will post the schedule. Okay. The schedule for 1 month, or else the schedule for one module, they will be posting it in your DFT group. So based on that schedule, it will be conducted for the basics training. For DFT advanced course, so as of now, this is how the schedules have been posted. Okay. This is how the schedules are actually followed.
Hi, ma'am. For advanced course in weekend, you are only the teaching, or any other instructor will be teaching?
For weekend, I will only be teaching.
Okay. What about weekend batch for labs, for level 3 and level 4? Can we understand in the online, or we need to come to lab?
So I both offline as well as online will be covered. So I will be handling it for the online batch. So if you want to enroll for offline training, so you can enroll for the offline batch.
No, I'm
If you're
looking for
comfortable.
no, I'm looking for only online batch, or weekend batch.
Yeah, it will be covered. You'll be able to understand. So
So
level
in
3 and
weekend
level.
batch, so it is, can I come online and both offline? It is our wish, right?
That you can once check with it, like check with the management, like Webhouse sir, you can check with Webhouse sir. So sir will be able
Okay.
to guide you on that.
Okay, okay, ma'am. Thank you.
Oh, so does anybody have any other queries related to the course?
Ma'am,
Yes, Navi.
the classes will be only for advanced topic of DFT. The classes will be only on the weekend, and remaining days it will be labs.
Yes, as of now, the theory sessions are conducted only during the weekends, and lab sessions, it is conducted separately. For weekend only students, separate labs will be there. For weekday students, separately the labs will be conducted during the weekdays. So as of now, the schedules are posted like that.
Okay, ma'am.
Uh, Ma'am, we are only working on Tezent tools, or any Synopsys or Tetramax.
So like
Mm.
in this course, we will be covering only the Tessent tools. So if you want like to learn, like we are also having Synopsys tools. So if you want, you can like get the videos of Synopsys tools, okay, from the
Okay.
institute, or else like if you just ask for some one-to-one session, like we can give you an overview about the Synopsys tools. But in this particular course, we will be covering only the Tessent tools.
Okay, we will get videos of Synopsys tools. Okay.
It's either
And
either videos, or else we can give you some one-to-one training, like to cover the synopsis tools and basics of synopsis tools we can cover.
for weekend batch, we can get recorded videos of recorded videos for.
Yes, everyone will be having the recorded videos. Everyone will be getting the recorded videos.
Okay.
Both for weekdays and weekends, you'll be getting the recorded videos.
Okay. Include in the lab, we can take by server VPN from offline online
Yes,
lab
you can take.
activities 24 by
Yes,
7.
yes, yes, yes,
Okay.
you can have.
Okay. When will be
Okay, so
the new weekend batch will start?
I'm not sure about it. Like, have you been added into a DFT group?
No.
Okay, like once you enroll into the course, you will be added up into a DFT group. So from management, they will be posting the schedules. Okay, so like yeah, regarding the course starting time and all, like I'll just share Usha ma'am's number. She will be able to guide you on that. Okay, so let me just share Usha ma'am's number. She will be able to tell when the batches will be starting for you. Okay, one second, I
Okay.
share the number. So I've shared Usha ma'am's number also. So anything related to the course fees or else anything related to like when your current batch will start both for weekdays as well as weekend, when the batches would be starting, you can just contact Usha ma'am. She will be able to guide you on that. Or else you can just contact the number which is given in the institute website.
Yeah,
Okay,
for
they will be able to tell you.
practicals, yes, ma'am. For lab practicals also there is recorded video.
Yes, both theory as well as lab sessions will be recorded.
Okay, okay.
Okay, so does anybody have any other queries? So like if you have any other queries, like you will be added up into an individual group as well with your VLSI Guru ID and your name. There will be a group which is created. So you can post your doubts in that group. We will be clarifying, we'll be addressing your doubts in that particular group. So there will be a group which will be created with your VLSI Guru ID and your name. So you can post your doubts in that particular group. Okay, so we will be addressing your doubts in that group. Okay, so does anybody have any other doubts now which you want to ask?
For weekend batch also same 6 months of course training curriculum.
Yes, same like same duration would be there.
Okay.
So the only difference is like here for weekdays, you will be having like labs we will be covering, labs will be covered, and then you'll be having separate practice sessions also where you will be practicing in the lab. And if you get any doubts or any errors, if you are getting this, you can get it clarified during the lab session itself. For weekend this for weekend labs you will be having only lab explanation sessions. So lab practicing you have to do it during the weekdays whenever you are having time, whenever you get the time you have to do the lab practice. And if in case you get any errors or any doubts if you have, you can either post it in your individual group or else you can get it clarified in the next session. Okay, so here for 2 sessions we'll be doing the lab test case explanation. So weekend, right? So 2 sessions for lab explanations. So for lab explanations, you will be having 2 sessions. So 2 sessions for lab explanations will be there. For weekdays, 2 sessions for lab explanations will be there. And then 2 sessions for same lab practicing. Whatever was explained here, the same lab will be practiced by you. So you will be practicing it in the same class. Okay. So lab practicing. Okay, lab practicing. Whatever lab was explained in these 2 sessions, the same lab will be practiced here. Okay, lab practicing session will be there. So that if you get, if in case they get stuck anywhere or if they get any errors, you can get it clarified in the during the lab session itself. But for weekends, you will not be having that lab practicing session, only lab explanation session will be there. So you have to watch this video and you have to like do the labs when you get the free time, okay, during the weekdays. And if in case you get any doubt or any errors, if you're getting stuck anywhere, you can either post it in your individual group or note it down and ask in the next class. Okay, so that is what is the only difference. So apart from that, the course completion time and all will be the same both for weekdays as well as for weekends. Okay, so if there are no further doubts, we can wind up today's session. Okay, so if you have any doubts, you can contact these numbers which I have shared in the chat box, or you can contact the number which is there in the institute website, or you can post it in your individual group. So there will be a group which is created with your VLSI Guru ID and your name. You can post it there. Okay, so yeah, thank you all. I will end today's class now.